Shivaji University, Kolhapur. He worked as a junior research fellow and senior research fellow under the guidance of Professor Dr. C.H. Bhosle and was awarded a PhD degree in year 2000. He had qualified state eligibility test examination in physical science in 2002, even though the results of the examination was only 0.1%. His research area includes thin films, solar cell, transparent conductive oxides, thermoelectrochemistry, gas sensors, photoelectrocatalysis, that is water purification. Till now, he has published 211 research articles in reputed international journals and acquired about 7,400 citations. H index of his publication is 51. He has successfully guided 14 PhD, 2 MPhil, and 59 MSc students. Currently, 5 PhD scholars are working by his department. He has published 5 books and filed 2 patents. He successfully completed 5 research projects worth 86 lakhs, which were funded by government agencies. He was honored for his contribution in research work by awaiting a life membership of Maharashtra Academy of Sciences at National Chemical Laboratory, Pune in 2000. Analytical instrumentation facility University Dharwad, PC College Baramati, Vivekanand College Kolhapur, Dattajirao Kadam Textile and Engineering Institute Italganji, JSM Rajashree Shahu College of Engineering Pune, and K.B.P College Pandharpur. He is working as a PhD degree for various universities, and he is a life member of Marathi Vignan Parishad, Association and Indian Association of Physics Teachers. Please start your speech.
Am I audible?
Yes, sir.
Yes. Good morning to
Yes, sir. Yes, sir. Good morning, sir.
Shall I share my screen so that it would be easy for me to start my keynote address. So let me share my screen first. Can you see my first slide?
Yes, sir.
Yes. Okay. Good morning to one and all. I have great privilege in addressing the one-day international seminar on energy storage and convergent devices being organized by Red Shikshan Samstha's Karmal Gaurav Patil College of Vashi. I am a product of Red Shikshan Samstha. Therefore, I am always happy to be a part of August gathering being organized by any branch of Red Shikshan Samstha. I was graduated from Science College, Lonand in 1992. Therefore, I am always delighted to be a part of the conference or workshop arranged by the college from Red Shikshan Samstha. So first of all, let me thank Honorable Principal Dr. Shubhda Naik Madam for entrusting me this opportunity to deliver a keynote address in this one-day seminar. I am also thankful to Honorable Head of the Department of Physics, Dr. B.P. Pujari sir, and his team comprising of coordinator Dr. S.P. Yadav sir, convener Dr. Archana Chavan, Dr. Ulka Suryavanshi, and other Shinde also is there, and other colleagues for giving me this honor. I also will be happy to note that in this one-day international seminar, the deliberation includes the lectures by the scientists from CMET Pune, Dr. R.S. Kaluvarme, the scientist from SRM University, Chennai, Dr. Balachandra Kakade, and the young scientist, Dr. Abhishek Lokhande from Coast, Abu Dhabi. Sir, as I was introduced by Dr. Yadav sir, I belong to the institute which is named after great Maratha warrior Chhatrapati Shivaji. So Shivaji University Kolhapur, which has got a evergreen campus, and it is a self-sustained water resources, and its campus is biodiversity rich. I'm heading Department of Physics, and I'm also working as in charge head of facility centers at Shivaji University Kolhapur. The title of the topic, recent trends in material research. This I have chosen because it overlaps with the theme of the seminar. Most of you may not be knowing the situation of the Shivaji University Kolhapur. It has been situated in the southern western Maharashtra on the Karnataka border, you can say near Karnataka border. Since last 25 years of my career as a researcher, I am working in the materials science or materials research area, wherein I have investigated both bulk materials and the material in thin film form. And therefore, my research fields, they were the porous high, ultra high light silica aerosols, composite materials for ME applications, chalcogenide thin films, tissue thin films, and all these materials they were prepared with the help of cost-effective chemical techniques and keeping a simple view of energy harvesting, conversion, and storage devices. We are using our materials prepared using cost-effective chemical methods for solar cell, gas sensor, catalysis, photodetector, and memristor application in my laboratory. So if you look at the publications by our group, you will see that most of them, they are oxides and chalcogenides. And the quantum of work in my laboratory is focused on solar cell, tissues, and the photocatalysis, gas sensors, and every composites. So materials is a broad and vital field of knowledge. Material science itself is a vital field of knowledge and research. And it is being the foundation stone of modern technological society. Therefore, one should talk on the material science and the research in material science and the current trend in research of material science. As all we know, this is an interdisciplinary field comprising of physics, chemistry, biology, computational engineering, civil engineering, chemical engineering, electronics engineering, where the focus is been understanding and utilization of the properties of the matter. People are constantly investigating new materials which can be substituted for the traditional materials for better application, efficient materials they are investigating. We know recently our government of India has announced National Education Policy 2020, where the idea of higher education institutes, where the research university and teaching university will be come up. But the main emphasis is given on the learning by research. So while they might have thought that research is very important in the education, what I feel, research itself is a creator of knowledge. And in research, the sense of research is being creating a new knowledge by resolving the doubts by creative study. And people come up with the innovative ideas. Students, they have their own ideas. Therefore, if we somehow inculcate the research attitude in the new budding minds, then the student, they will find their own way of learning. They will be self-reliant as far as education is concerned. Therefore, research is very important aspect in the forthcoming education system. Let me spare some time to tell, because most of the students, they are postgraduate and graduate students. Let me tell what after all is the motivation of the research. Most of the people, they have got their academic interest and they work for getting degree and placement, and they are motivated, but they are desired to get a degree. Few desire to get intellectual joy by doing research, and for that they do some creative work. Few people desire, by doing research, they think they will serve the society and get respectability. And few people have the ultimate aim of solving the unsolved problem. Many problems, many questions are there in our nature. So they wish to address this problem. They wish to find the solution for this problem. And these solutions would be useful for the betterment of the society. So this has been the motivation of the research in any branch. And as I told, the research takes you from known to unknown. It gives you the opportunity to gain a new knowledge. It is the art of scientific investigation, and these investigations, they are careful investigation for finding new facts. So here are a few steps in research. Those who have already done research, those who have already completed their PhD degree, they might be familiar with this. But for those who are newcomers in the research, for them, so research has got its own path. We initially formulate a hypothesis for a problem. So for formulating hypothesis, you should have something in your mind. There should be some question. There should be some something that you think this issue should be addressed. So for that, you need to read the literature. So you should have some foundation knowledge of subject, and based upon your thinking and thought process, you formulate a hypothesis for research. Based upon the hypothesis, we define a problem. We define a task that such and such thing we need to address. For that, if it is a research from science, then the scientific method includes collecting, organization, and evaluating data. And this data, based upon this data, some conclusions are made, and then the hypothesis is tested. So this is the way, the steps in any research. As far as research in material science is concerned, then we need to address some, we come across some major challenges in material science research. Namely, the fields which we need to address, they are energy, environment, security, infrastructure, transportation, and health and welfare. So people, the major challenge in the material science, as far as energy topic is concerned, people are investigating different materials for generation, conservation, and distribution of energy. As far as environmental issues are concerned, your material synthesis process and their application strategy, they should be environmental friendly. So they wish to develop a clean source of energy. They wish to develop a clean water. Then there are few climate changes, or the climate changes due to harmful gases of the material scientists. So far as security of the nation is concerned, we need to develop the diagnostic devices or the sensors or the protection systems. We need to develop soft and hard, lightweight armor materials. We need to aim to develop materials which are used in the batteries and power sources for portable security devices. So these are some of the major challenges in front of the material scientists so far as energy, environment, and security sector of the research is concerned. As far as infrastructure is concerned, aim should be to prepare a material or the mechanism for defending from the natural disasters, accidents, terror threats, etc., etc. Also, our transportation system should be uplifted, upgraded, and we should develop a material so that they are low cost, and therefore the vehicles prepared out of these they will be low cost vehicles. As far as health and welfare is concerned, we aim at development of production of systems from sports and other injuries material textiles, packaging materials for both better food safety, orthopedic implants, and limb replacement for tissue fixation and bone repair. These are some of the challenges in front of the material scientists as far as health and welfare sector is concerned. So here I have shown the cornerstones of the material paradigm. So when we try a research in the materials, then material need to be processed, prepared, it needs to be characterized, it should be characterized in terms of its structure, and we need to study its properties, keeping in view some application. So sustained efforts in the research of material science are concentrated in designing and discovery of new material. As I told, people are constantly working on investigating new materials. And these new materials, they should be lighter, faster, stronger, smarter, and durable than the existing materials. So characterization techniques, in the modern characterization techniques, they play a key role in processing and testing the properties of the material. Which are the properties? Once the material is prepared, synthesized, then as far as microstructural, macrostructural, submicrostructural, crystal structure, nuclear structure, and electronic structure needs to be looked upon as far as material is concerned. When we study properties of the materials, then we need to look for mechanical, thermal, electrical, magnetic, optical, and chemical properties of the materials. And the aim should be use of these new materials in various applications in the subject physics, chemistry, life science, engineering, and industry. There are thousands of or lakhs materials known to the mankind. These materials, they are natural materials. Either they are natural materials or they are man-made materials. Natural material like wood, human-made material like plastic. So there is a list of more than 3 lakhs different materials. And of these, the people there have extensively studied these materials. Here I am giving a representative list where the 6 or 7 types of the materials I have chosen just for the sake of addressing. Include magnetic materials, superconductors, thermoelectronic materials, supercapacitors, energy devices, electronic materials, biomaterials, semiconductor materials, graphene, polymers, composites, nanomaterials, optical and photonic materials. So one by one, I will take the review or just glimpses of these materials and what is being done as far as the area of these materials is concerned. We know the permanent magnet. Material is magnet. It exhibits magnetic property due to unpaired electron that we know. It has got a resultant magnetic moment, and based upon the value of this magnetic moment, materials are divided into paramagnetic, diamagnetic, ferromagnetic, ferrimagnetic, antiferromagnetic, etc., etc. Out of these, the ferromagnetic materials prepared out of iron, nickel, and cobalt and their alloys, they are conventionally used in the permanent magnets. But for these materials, recently they have investigated a new materials called as new generation materials. Owing to their cost, their operating temperature is very high. Their corrosion resistance is very high. Their strength also is very high. As you can see, compared to steel, for example, if we see the relative magnetic volume for the same magnetic energy still has got maximum magnetic energy, and of course relative volume is high than the NdFeB. This is a new generation magnetic material. So new generation magnetic materials, they are AlNiCO, SmCO, NbFb, and other few, and list I have given here. So the people, they use them in the storage media, robotics, and sensing material, sensing sound. So permanent magnetic materials, they play a very important role in the storage media that we know. Superconductor is the another class of the materials where people, they are extensively investigating the new temperature of the superconducting materials. We know ordinary conductors is converted into superconductor at particular temperature. If you decrease temperature of the conductor, then the ordinary conductor behaves as a superconductor where it loses its all resistance. And this phenomena was invented by K.B.P in long back 1911 in case of a mercury, where they found that mercury behaves differently at 4.2 K also. So since then, research in superconducting material is continuously going on, and people are investigating a new material where the TC, critical temperature of the superconductor, is relatively higher and higher and higher. So in 1986, a new class of material as far as superconductors are concerned, based upon YBCO, DISCO, and other systems, the critical temperature was around 70 to 80 K. They were categorized as a high DC superconductor. The high word higher than 4 K, therefore high DC superconductor. Recently, a new material like lanthanum decahydrate, where critical temperature is of the order of 250 K, still not, keep in mind, room temperature or 0 degree Celsius. It is still below room temperature, minus 23 degree centigrade. And the efforts are being concentrated on synthesizing higher TC superconductor, maybe room temperature TC based superconductor. And this is the list of the materials where niobium nitrate, magnesium decaborate, yttrium barium copper oxide, strontium rutheniate, sodium cobaltate, pyrochloroxide, niobium carbide, boron carbide. These are the materials people are constantly investigating. Thermoelectric materials, where we know these materials converts heat energy into electrical energy. If there is a difference, a material is kept at two different temperatures, then the potential is developed across it, and vice versa. We know Seebeck observed this effect long back. So creating temperature and current, voltage can be created. So such materials, they are called as thermoelectric. This effect is called as thermoelectric effect, and the materials which are used for this effect is called as thermoelectric material. Now, people are investigating new materials, the new thermoelectric materials such as Bi2Te3, PBT, SiG, Sb2Te3, etc., etc., where they link the synthesis criteria or the structural characterization and properties and the science of these materials. And what, after all, the aim is these advanced thermoelectric materials would improve the refrigeration efficiency of the air conditioners and freezers. Energy storage is very important. We know the energy can be converted from one form of energy to other form. Solar energy can be converted into electrical energy. It can be converted into chemical energy. But for example, if you convert solar energy, and if you wish to use this converted solar energy at a later time, then you need to store it. And this, the only way is to store it in the chemical energy form. And we know the storage media for saving energy, storing energy in the form of chemical energy, we need a kind of a battery. And therefore, research in batteries, particularly these batteries, these are lithium-ion battery, lead-acid battery, etc., etc. It is continuously going on, and these batteries are now replaced by the supercapacitor because it bridges the gap between capacitor and the batteries, where it has got higher specific energy and higher specific power. So supercapacitors are used in the rapidly charging discharging devices, and rapid charge discharge cycles, they are there, and we should look for the material, supercapacitor material, where this supercapacitor material will stand for this rapid charge discharge cycle. And of course, durability is the issue. Current research in the energy storage devices, where ruthenium oxide, manganese oxide, these are the traditionally studied supercapacitor material, but people are working in polymers and the composites and the carbon materials, nanomaterials, where the composites formed between the metal oxide and polymer or carbon and graphene, etc., where the aim is developing pulsed power capacitors for charging of storage batteries for hybrid vehicles. And people have achieved very high specific capacitance in the storage devices. Energy harvesting and storage devices, particularly if we want to use the solar energy for the fruitful purpose like degradation of organic molecules or purification of water for generation of hydrogen, based upon the photoelectrochemistry, then the materials like titanium, tungsten trioxide, zinc oxide, barium titanate, they are, and their composites, they are extensively studied. So photocatalysis is one of the examples where solar energy is used for degradation or purification of water. So this is a small prototype reactor where the thin film photocatalyst is deposited on the transfer conducting oxide, which is being deposited on the glass. And in this assembly, a metallic counter electrode and the bias is applied between anode and cathode for effective charge separation. So from here, impure water goes, and from there, relatively pure water comes. And if you continuously do this recirculation, keep this in the recirculation mode, then it is possible to remove organic impurities. These impurities, they cannot be removed with the help of conventional water purification technique. Therefore, photocatalysis, based upon TiO2, Fe3O3, zinc oxide, and tungsten trioxide, this also is a very attractive field of research. Recently, graphite, carbon nitride, copper oxide, and bismuth vanadate, these are the materials as far as metal oxides are concerned. They are extensively investigated, and research trend and opportunities in the catalysis is centered upon these materials. And not only commonly used semiconductor metal oxides, but they use organic materials also. So they have a combination of organic, inorganic photocatalysis. So organic semiconductor photocatalyst, then inorganic semiconductor photocatalyst, and their composites. So people are working on these type of materials also. SOFC, solid oxide fuel cell. We know fuel cell is a material which converts chemical energy into electrical energy. And the chemicals are gases, for example. Solid oxide fuel cells, the fuels being gases. For example, oxygen, hydrogen, and other gases. When these gases, the oxidation reduction reaction occurs and the electricity is generated. And if this fuel is a solid oxide, then it is called as solid oxide fuel cells. And popular electrolyte materials, solid oxide electrolytes used are YSZ, SCHZ, and GDC, where the efficiency achieved is greater than 60% and operating lifetime is greater than 40,000 hours. And so this also is a very attractive field, solid oxide fuel cell. People are investigating the materials for anode, cathode, and electrolyte. Optoelectronic and photonic material based upon direct band gap materials like gallium arsenide, indium phosphide, 3,5 semiconductors particularly. So these materials are pivotal significance due to their frequent use in the electronic gadgets, PCs, hard devices, etc., etc. And which are these devices? They include laser diodes, superluminescent diodes, light emitting diodes, photo detectors, imaging detectors, etc., etc. And the devices and gadgets based on the spintronic materials, they have the materials like metal, insulator, and metal. So three layers are there, and people are investigating the semiconducting oxide, where such kind of attractive gadgets are made with the help of spintronic materials. And these materials, this is the list of the materials, some multiferrite metal oxide, multiferrite materials, ferrite, these are new kind of ferrites, are tried in these spintronic devices. We know nanotechnology has changed overall face of the material science research. And people are investigating three-dimensional, two-dimensional, one-dimensional, and zero-dimensional nanostructure. If you take an example of carbon in the different forms of the nanomaterials, the three-dimensional form is graphite, two-dimensional form is graphene, one-dimensional form of the carbon is carbon nanotube, CNT, and zero-dimensional form is fullerene. So people are investigating all kind of nanostructure of the carbon and other materials. And these materials, they have got tremendous applications because we can tune the material property just by tuning the size of the materials. And these applications include optical, magnetic, catalysis, microelectronic, pharmaceutical, storage technology, and energy. Almost all fields of science and technology, we can use these nanomaterials. Nanomaterials such as one-dimensional nanostructures such as the wires, fibers, rods, and tubes and builds, they have got tremendous applications in energy storage, absorbents, catalysts, and sensors. There are few materials like scratch resistance Corning Gorilla Glass particularly, and thermal insulating composite materials which are used in the aerospace technology. They play a very important role. And these materials, they are ceramics and glasses. The thing which makes them very resistant to the damage is diffusion of potassium ions far into the surface, which creates high corrosive stress. As far as polymer technology is concerned, it has got applications in textile industry, aerospace industry, automobile industry, electronic and electrical industry. The polymers such as PANI, PPY, PT, PSC, polyfuran, polyzylene, etc. So as far as current research in the polymer technology is concerned, so people are investigating these materials in the different forms, and they are forming composite of the polymers with the metal oxide and other materials. CNT, carbon nanotube, as we know, it has got large number of applications. So they can be single-walled carbon nanotube or it can be multi-walled carbon nanotube. And this has got tremendous applications in medicine. So carbon nanotubes, they are extremely high specific strain and they have got high modulus. And their multifunctionality in paper and textile industry makes them very attractive material in the various applications. Computational material science research is a new field, emerging field, where we compute and design a material on a computer. And after designing material on the computer, we save our lot of time in tailoring the material properties. The material properties can be simulated. So the very well-known method used for computing or designing the material as far as computational material science research is concerned, they are DFT, that is density functional theory, molecular dynamics, kinetic Monte Carlo, dislocation dynamics, phase field, crystal plasticity, finite element method. These are the few methods which I have listed as far as methods for designing a materials is concerned. So what actually we do, we compute experiment based upon the theme. So this also is very attractive field. Graphene, as we know, is a two-dimensional trough of the carbon, and it is the strongest material. It efficiently conducts heat and electricity. And discovery of this graphene has provided an immense boost in nanotechnology research. Currently, they have focused their attention on modification of graphene to enhance its application potential in different areas of nanoscience and nanotechnology. And graphene has got large number of applications in sensors, aerospace, high-speed transistor, tissues, energy application, and flexible electronics. Quantum dots. These are referred as the artificial atoms. Dot means one atom, and it can be referred as a quantum dot. And the quantum dots of 3-5 semiconductor, particularly in gallium arsenide, indium phosphide, indium arsenide, etc. And the applications are based upon the spin properties of the single electron. And the current status of research in this field is realization of highly controllable quantum dots, where the potential applications are single electron transistor, solar cell, light emitting diodes, and quantum computing and medical imaging. Biomaterials. Of course, I am not expert in the biomaterials, but the biomaterials like silicon rubber, decaron, cellulose, polyurethanes, etc. These materials or the biomaterial field focuses on development of these materials to replace human tissues and human organs. So this is also a great field, and people are working on these biomaterials. Once the material is prepared, this advanced characterization tool makes them materials more beautiful based upon, for example, the advanced microscope, spectroscope, and the testing equipment like HRTM, APSEM, spectroscope, and etc. So it is possible to test the material properties in situ. So in situ physical properties measurement system have facilitated researchers to do in-house multi-measurements on their samples, and therefore material science research has become more feasible. So this is the list of the materials, some materials. So what are emerging trends in the material science? What people they are focusing attention to? So there are many emerging trends. So only few I have listed here. And the fields are silica aerogel, conducting polymers, fullerene, thin film devices, 3D printing, nanoscale machining, titanium in aerospace industry, and perovskite solar cell. So let me give you some glimpse about this material. So silica aerogel is a very attractive material, and it is porous, it is ultralight material, where within this material about 99% air is there. Only 0.2% solid material is there. And these materials, they are not only light, but they are transparent also. And the density is very, very low. And therefore, they are applied, they seek application in thermal insulation, liquid rocket propellants, supercapacitors, carrier for catalyst, active agents, filling materials, material for tissue engineering, etc. These are some of the applications of silica aerogel materials. So future prospect of this material, so people are investigating inorganic silica aerogel, that is SiO2. But people are focusing on the organic material like RF, resorcinol formaldehyde, and the hybrid materials like the organic, inorganic aerogel materials. Conducting polymers is another emerging trend or the material where the discriminating layer in the electronic chemical sensor is the conducting polymer. We know polymer can be insulating, can be semiconducting, or it can be a metallic. But the conducting polymer, like traditional plastics or polymers, are the electrical insulators. But people are investigating new polymer material who conducts the electricity. Fullerene, as I told, it is one of the nanostructure of the carbon. So for drug delivery system, fullerene can be used. Thin film device is a very attractive and very important thin film, what you can say, next generation memory and processor field. So where the applications which we are looking, which we are investigating in our laboratory, they are use of these thin films in solar cell, transfer conducting oxide, memory store, photocatalyst, gas sensor, etc., etc. So these thin films, they are the material whose thickness is less than 1 micrometer also. So a material, when its third dimension is restricted, it is defined as a thin film. And these thin films, they have achieved technological breakthroughs in the areas like recording media, semiconductor devices, light emitting diodes, optical coating, hard optical tools, energy generation, energy storage, and even in the pharmaceuticals. So far as research in thin film is concerned, we need to prepare a thin film. So there are a variety of techniques of preparation of a thin film. There are physical methods, chemical methods, of course biological methods also are there. But these methods, they are broadly classified into two areas or two types, physical methods and chemical methods. Physical method include vacuum evaporation and sputtering, and chemical method include gas-phase chemical technique and liquid-phase chemical techniques. And this is the list of the techniques where the material can be prepared with the help of various techniques. Out of these, the physical methods, they are vacuum evaporation and sputtering. Why these methods are called as physical method? Because only physical form of the material is changed. Solid getting converted into vapor, vapor again condensing into solid. So physical state of the matter is changed in the physical method. But in chemical method, the chemical reaction occurs between two chemical compounds and new material is generated, prepared, fabricated. And therefore the name physical and chemical. But these physical methods, vacuum evaporation and sputtering, for example, they have got disadvantages because they are costly. They require vacuum for their operation and they operate at very high temperature. They are time consuming and requires cooling system. So chemical method is the another alternative. In this chemical method, gas-phase method also require very high temperature and they are not environmental friendly, where the chemicals, ingredients, they are taken in the gaseous form and they are passed over the sample where degradation takes place, decomposition takes place, and material in the thin film form is prepared. But these methods, for example, CVD is the technique. So these are not environmental friendly methods and they operate at very high temperature. So gas-phase chemical methods also has got some disadvantage. Therefore, people go for liquid-phase chemical method, namely the CILAR, hydrothermal method, chemical bath deposition method, spin coating method, dip coating method, spray paralysis, and other few techniques. So these methods, they are simple, they are cost-effective, and the material properties prepared or the properties of the material prepared with the help of chemical method are comparable with the properties of the same material prepared with the help of physical and other technique. So this is one field. Another field, emerging field in the research of material science is the 3D printing. So we know printing, we know laser printing, we have a printer in our lab. So ink is being spread in a raster manner, is it not? It goes like this, then come down, then goes like this, but it forms only one layer. But if you prepare a printer in such a way that it is possible to print a material in the 3D form. So popular modes and jewelries, they are printed with the help of 3D printing technology. So material is architectured on a computer and it is being printed three-dimensionally. So in gift industry, in personalized art gallery, this 3D printing is used. Nanoscale machining using a tip or in the atomic force microscope, it is possible to tailor the properties of the material you choose a type or the positions of your atoms, and you can tailor-made the properties with the help of nanoscale machining. As I told, titanium in the aerospace industry is a very attractive field where lightweight and strong and versatile components of the aircraft like wing, then landing gear, door, engine, and other structural components they can be formed, prepared with the help of titanium. So this also is a new trend. And the field, perovskite solar cell. So this solar cell, we know there is an N-type material and there is a P-type material as far as the solar cell is concerned. But this N-type and P-type material, or the solar cell prepared with the help of traditional semiconductor material, they have got the limitations as far as efficiency is concerned. And we cannot avoid the combination of generated electron and hole. So this can be effectively met if you make a configuration like on the glass substrate, there is the F2 and there the TiO2, and then this ternary perovskite material is there, and then anti-reflection coating, and then the top contact. If you prepare such kind of solar cell, then it is possible to achieve the efficiency of the order of say 33 or so. So this perovskite solar cell, they can be organic perovskite solar cell or they can be inorganic perovskite solar cell. Inorganic perovskite solar cells means ABO3 like materials. But the organic materials like methyl ammonium, lead trihalide, and other organic structures, or they are used in preparation of perovskite solar cell. So the most efficient band gap is found to be around 1.34 electron volt, and maximum power conversion efficiency of the order of 33 has been achieved with the help of perovskite solar cell. So this also is a very attractive field in which people can work. So this was a whole story of the current trends in research in material science. So I should acknowledge my research group, Electrochemical Materials Laboratory. You can see the photograph of the coordinator of this conference, Dr. S.P. Yadav. And attached to all my research scholars. And the research index, which I have achieved now, it is all due to these young guys. Thank you very much for your patience listening, and I will be happy to answer few representative questions based upon my presentation.
Thank you, sir. Dear participants, please drop your questions in the chat box or you can ask yourself. Just unmute yourself.
You can ask me the questions in the chat box. Are there any questions?
Not yet, sir.
No. So I request the participants, because there are more than 90 participants.
Sir, there is
They
one
can
question
ask them. Yeah. Please,
from
please.
Dr. Paviskar, sir. He has asked, which is the best perovskite material?
So I am not actually expert as far as perovskite solar cell material is concerned. I am expert as far as tissue material is concerned. But the best perovskite material, the list which I have given in this list, I can tell you the best material to be based upon CS3, NS3, PBX3, methyl ammonium, lead trihalide. So this was the material for which they have achieved the efficiency of the order of 34. So this can be the best material, and because this I have collected from one of the review. Therefore, recent review I have not seen, but it can be other material as well.
So there is one more question from Dr. Chandekar. What would be the power conversion efficiency if we use double perovskite material?
No, the efficiency of these perovskite solar cell materials or solar cells, it depends on many factors. It is not a question of connecting two solar cells in series or parallel, because he says what will happen to efficiency if we prepare double solar cell. So he meant to say that two solar cells are connected in series, or what is the question? Double solar cell means
Double perovskite material.
double perovskite material, of course. Double perovskite material will add to the difficulty of the charge transfer mechanism. So better we use a single perovskite material. But double perovskite material will not improve the efficiency, but they can form the composite between two perovskite materials. This is possible. But two layers of two composite materials, two perovskite materials will not improve the efficiency.
Bhaviskar sir, with his previous question, has asked can we grow the material using chemical route?
Yes, we can grow the material with the help of chemical. I have separate lecture on chemical methods, and I have talked to more. So it is possible. It is possible with the help of chemical method. We can grow any kind of material for many applications, and we are investigating many applications. And my whole list of the publications, more than 200 publications we have made, all the materials they are prepared with the help of chemical methods. So yes, it is possible.
Next question is by Mr. Kailash Jagdev. Is carbon solar cell practically possible?
Carbon, you need to make it a semiconductor. Then it is possible. Yes, it is possible. But you need to make it in such a way that it acts as a semiconductor.
Next question is
Nirmala Varmade has asked, can any oxide material is possible to prepare using CPD method? Certainly, this chemical part deposition method is a low temperature method. Therefore, directly we cannot prepare oxide material with the help of chemical part deposition method. But what we can deposit with the help of chemical part deposition method is a hydroxide of corresponding compound, and then subsequently this hydroxide can be sintered, can be oxidized, and then oxide materials can be formed. So directly, without post-preparatory treatment, it is not possible to prepare oxide material. Chavan, you are asking some question.
Am I? Okay, sir. Actually, as you said, the solid oxide materials are some electrolytes are there for the solid oxide materials.
Right.
But if I will use that electrolyte, or that assembly as a gas sense, can I use that one?
Means you want to replace this electrolyte as a gas?
No, sir. That assembly, anode and electrolyte assembly, can I use that assembly as a gas sensor?
Yes, we can use. What after all the gas sensor is, if the material changes its property due to exposure of a gas, if the junction between gas and solid, if it is there, and if we expose that gas and that material, if it is kept at high temperature, then you need to monitor the properties of the material on which this gas is exposed. Yes. So yes, it is possible, because dual device you are talking of, is it not?
Yeah. Yes.
So it is possible.
Good morning, sir. Ulka here. Sir, I'm having one question. That is, what is the main challenge in front of solar cell research, whether it's efficiency or cost effectiveness, and what is the exact role of different structural morphologies on the efficiency or cost effectiveness?
These are a couple of questions. Efficiency is limited by many factors, and the main factor, the efficiency, after all, efficiency is? Efficiency is for one photon, how many electron and hole pairs are generated. We create one electron and hole pair. Is it not? But it is not possible. It is not possible to make these electron hole pairs as a useful electron hole pairs. So for 1,000 photons, 1,000 electron and hole pairs are generated. Out of this 1,000 electron and hole pair, only 50 are useful. So you need to create a situation in such a way that you need to use, or we can use, all electron and hole pairs. So this is one. Efficiency is, so recombination you need to avoid somehow. This is one. And other is the cost effectiveness. Yes, the solar cell based upon the silicon materials, they are costly. And if you want to prepare the modules out of the solar, this silicon solar cell, then silicon fabrication or purification of silicon itself is a very costly technique. And that's how the cost of the solar cell is increasing. Is it not? Therefore, if you prepare, or if you investigate a material which is substitute to the silicon material, or you can think of thin film solar cell material, then also the cost can be reduced. You can go for chemical methods for preparation of a solar cell. So these are the answers to your two questions. And what was your third question, Vulkar?
So what is the role of structural morphologists? Means we use from nanomaterials to mesomaterials. So what is the exact role?
The role of nanomaterials in the solar cell research is that by making use of nanomaterials, you can avoid the recombination. So this is the role.
Okay, sir. Okay. Thank you so much, sir.
Okay.
Participants, do you have any more questions?
So if there are no further questions, I would like to thank organizers, particularly Dr. Chavan and Dr. Yadav and Principal Madam for giving me this honor to address this together. Thank you very much.
Thank you, sir. Thank you very much. With this very informative keynote address, we will move towards our next session. May I request Dr. Paresh Gaikar to introduce a resource person of the next session.
Good morning to all. I am Dr. Paresh Gaikar, Assistant Professor, Department of Physics, Dharmavir Bhaurao Patil College, Vashi. Our today's speaker, who published more than 70 international research papers in international journal, as well as 7 patents in his credits. Currently, he is working on 3 self-funded projects and 1 industrial project from Tanish Titan. It's our pleasure to have such a great personality as a research person with us. The renowned researcher in India, Dr. Bhalchandra Kakade sir. Dr. Bhalchandra Kakade sir is currently working as an associate professor at SRM Research Institute, SRM Institute of Science and Technology, Chennai. He has worked as a postdoctoral researcher at the Tokyo Institute of Technology, Japan, during 2008 to 2012. After his doctoral degree at NCL Pune, India, his research work is primarily focused on low temperature fuel cell catalysis, especially oxygen reduction reaction and methanol electrooxidation. He has also expertise in chemistry of carbonous material and their nanocomposite, layered double hydroxide, noble metal free materials, and so on. In addition to that, 7 PhD scholars are pursuing their PhD degree under its guidance. I am sure he will enrich us about energy storage devices with his knowledge on fuel cell. Over to you, Dr. Bhalchandra Kakade.
Thank you very much. Am I audible?
Yes, sir, you are audible.
Thank you very much for, first of all, organizers for giving me this opportunity to present some of our recent results. And I will be happy, whenever I'm present in front of our people, like Kolhapur, Pune, Mumbai. I enjoy a lot, especially with the students. And sorry for joining a little late, but okay. So this is the. Can you see my slides?
Yes, sir. Yes, sir.
Yeah. So I'm talking about next 45 minutes about the fundamentals of the electrocatalysis for low temperature fuel cells and their applications, and what we are doing currently with my whole team. So first of all, I should thank my whole team. This is like picture of our group. If you are missing here, so all the JRF and SRF students and postdoc, and who are completed PhD and they have joined some postdocs. And I should not forget about the great help by SRM IST, GST, SCRB, YSL, GST, SRB, EMR, MNRE, Government of India, Titan, Tanish, all these are the funders for my projects. And because of that, we are doing smooth research work here. So again, I should not forget about the contribution made by our foreign collaborators, especially Professor Yamaguchi, Professor Gunther and Tamaki, and so on. Then with this, acknowledgement, I should talk about what is today's recipe in front of you. I'll be talking about brief about the energy conversion, how it is happening in case of the fuel cell, especially low temperature fuel cells, and what is the current progress in the fuel cell technology, and what are the issues like oxygen reduction, what actually is the oxygen reduction reaction, how the alloy nanocrystals of platinum play an important role in minimizing the potential of such reactions, and our ORR studies, what we are doing in the laboratories, and the stability tests are very important. And finally, I will take your queries and we will discuss more on that. So this slide is very important for our students, right? When we are entering into the research or any problem, we are going to face in the future as well. The first question is, what is the problem? Actually, when we select any problem and we are trying to find the solution, 4 questions are very important. The first thing, why? We should ask the question why we are doing it, why it is important, whether this problem is important or not. And the second one is whether it is interesting or just boring. If it is interesting, then it is better to go ahead. Otherwise, you should get rid of this. So any problem, to find out the solution. So first question is why this question arises first. Second one, it comes with whether the problem is interesting. Is it what to solve this problem? Is it interesting? Then third one, which is very, very interesting and very important, as far as the day-to-day life and the current situation, whether the problem is cutting edge. Cutting edge in sense, is it a hot topic? Whether it is relevant to the current problem, whether let it be like a socially you take, economically, financially, anything you take, whether it is relevant or it is a cutting edge or it is a hot topic. And the last and very important is whether it is a new solution, whether you are going to do it. Are you able to solve this problem? Are you going to provide a solution? If all questions, if you solve this, why, whether it is interesting, whether it is a hot topic, or are you going to provide a solution, then the problem is solved. That's all. That is the research, what we do, right? Any simple example you take, when you try with the literature survey, the why, you should ask the question why it is, whether it is interesting, cutting edge. Otherwise, if you take a very old and very boring subject, you will not get a proper solution as well, and you cannot solve this problem as well, and it's not interesting. So if you solve this systematic all the questions you should ask yourself, then that's it. That is actually a solution what you get, and you can do a better research in future as well. With that, I should move to the next important slide with what are the different challenges in the next 50 years. So if you see that all these I have made a different bullets, starting with the energy, water, food, environment, poverty, terrorism and war, disease, education and population. If you think of everything, every single entity into this, all are going to be very challenging in the next 50 years. So we have a lot of challenges in next 50 years. At least one by one we can catch into that. So here I'm not going to go into more details of other things, because it is really challenging to solve one by one itself. So I will be focusing on the energy. You can see that this is the planet. It means that all these parameters, what we are going to study, it is in our hand. The whole planet is in our hand, and how we can avoid to burn it from both the sides, right? So I will be talking about mostly on the energy. So energy is very important. It is going to be a challenge in the next few years as well. So it is very familiar picture. If you start from how the energy is being a basic need for humankind and other sectors as well. So this is very familiar where our mothers and grandmothers used to cook our food on the chula, and then it went to the gobar gas, then it again combustion gas, then slowly it come to the electrical things, and like this gaseous one, then we came to the electrical, then again microwave and so on. So slowly how we moved from our like a fossil non-regional energy sources to the electrical one, which is a completely different era. So we are entirely dependent on this electricity. Without electricity we cannot move at all. So what is the summary of this? We're starting with the a wood and cow dung, then we came to the fossil fuel here, then eventually we cannot live without the electricity. The electricity become unavoidable part of our lives. If you take an example, if you are not keeping the cell phone with you for just 2-3 hours, you become restless. That is actually effect of our electricity and everything together, overall ensemble effect. So why we need this, right? This is a very important question. Why do we need the renewable energy? Now, currently our planet gets most of its power from coal, oil and gas. These so-called fossil fuels were formed from the remains of living organisms existing millions of years ago. We know everyone. And when these are burned, release heat energy that can be turned into electricity. Okay, that we know it's a very familiar picture. So many years we are doing it. However, they are also very harmful to the environment, as burning fossil fuels also gives off a lot of carbon dioxide, sulfur dioxide, NO2, and so on, a greenhouse gas that contributes to global warming. That is a very daunting challenge in front of us right now. As the sun's energy beats down on the earth, approximately 70% of its get absorbed by the land and the oceans, right? Remaining 30% reflected back into the space, right? Then, however, the 70% of the absorbed by Earth is eventually radiated by gases, right? Radiated back into the atmosphere in the form of infrared radiations, right? And greenhouse gases then absorb this energy, but also emit heat in this process. So what happens? These greenhouse gases absorb these infrared radiations and the heat energy, which warm the Earth's surface and lower atmosphere. Okay, this process occurs naturally and is what keeps the planet warm enough for living things to survive on it. However, a dramatic increase in the greenhouse gas emissions since the Industrial Revolution has also caused a big rise in the average surface temperature of the Earth. So we have seen the consequences of that. You can see that after a few years, these oil reservoirs, like if you say, for example, 50 years, all reservoirs will, run out of their, stocks. If you think about this coal, almost like a 250 years, next 250 years, it will, completely run out of their stocks. So then we have to think about what is the next option for that, right? So then we have seen the consequences of all these, what we are contributing into the atmosphere by burning so much, carbon into the atmosphere. So what is happening? This in turn has caused the worst glaciers and ice shelves to melt faster. All the ice from the Arctic and everything is melting. We are getting a rise in the sea level. We are getting heavy rains. We are experiencing this is a heavy fog into the capital of India. This is a recent flood in the Chennai near the coastal areas. For example, apparently we are witnessing an increase in the global temperature that adds on the fierce and devastating tropical storms and hurricanes, and could also trigger severe droughts in many parts of the world. These are the actual consequences of what we are disturbing the atmosphere. It is the man-made problem, right? So again, in addition to that, if you see in the capitals, mostly the capital cities of India, globally air pollution, this is a little old data, but it is relevant to understand that globally air pollution caused more than 4.2 million premature deaths in 2015. It's very alarming number. 4.2 million number is not a small one. It is just because of the pollution, air pollution. Other pollutions are separate from this. So as many as 92% of the world's population lives in areas with unhealthy air. So these are the other problems. This is not a platform to discuss about all the consequences of the air pollution, so on. But all this scenario is very alarming. And then the time comes to think about the green, right? Everything should be green. This is a very interesting scenario. What we have seen there. This is just on November 2019 picture we have taken, and you can see that after that, just 4 months, 30th March 2020, the same place in the New Delhi. What you have seen there. What does it mean? This is what message is given by the actual nature, like Mother Nature. So if you can't do that, I can do this. So that's what the COVID-19 came into the picture, right? This is the COVID-19 effect in the Delhi. So it is a man-made problem. If nature says that, okay, wait, I will do that. So this is what it cleans it with the expenses of almost 8 to 9 months of our lives got distracted and so on. So one has to understand. Everybody should be very aware of that. What we are going into the giving into the atmosphere. What is our contribution? We have to think 100 times when we are throwing a small piece of paper on the road. It is going to be a pollution into the atmosphere. So this is everybody's responsibility to avoid the pollution, any kind of the pollutions, right? So this is a very simple and very important example of the picture in November 2019, and within 4 months we have seen this clean city because of the COVID-19. One more thing, then it is very important to study that. This is again a very interesting, representative picture of the Google, and we know that Google is being the world's largest search engine, right? Google, processes almost 1.5 billion monthly searches. It's more than that actually. It's a little older data, and you can see that if I click once, just click once, let it be on your cell phone or your laptop or your desktop. If you click it, it requires like a 0003 kilowatt hour of the energy. And by generating this much energy, you are going to contribute 0.02 grams of the CO2 into the atmosphere. See, it looks very small one, right? For a single click. Now you can imagine that everybody's almost getting 1.5 or 2 GB per day. You can see that how many clicks we are doing it and how much carbon we are putting into the atmosphere. So that much energy is created by this. These are the representative examples. Now you can think about all monthly Google searches, clicks. See that how much the enormous amount of the energy is required to click that, and it consumes this much energy. And for generating such a big energy, you are going to make to 60,000 kilograms of the CO2 into the atmosphere. See, a single clicking a Google, we are adding this much carbon into the atmosphere. Then think about other automobile industry and so on. So isn't it a right time to think about green thing? So what we're doing eventually, if you think about this October 2018 data, CO2 is at 407 ppm, increased by 90 ppm in the last 70 years. Global warming rises almost 1.1 degree more than last 200 years. Acidification of the ocean is happening. Rising sea levels by 3.2 mm each year is happening. There is a decrease in the ice sheet mass, retreating glaciers, decreasing Arctic ice at a rate of 13% each decade. So these are, look like we don't directly feel the problem where we are sitting, but it is a really alarming. Okay, so this picture gives another information about, right? We may think that even if burning fossil did not have this destructive power, it would still be important for us to find alternative sources of the energy. Even if you think that it is not going to make so much problems in the atmosphere, but still we need to look in the more renewable and more green approach for the energies. Although fossil fuels are technically renewable, as they are made from the living organisms. How we make the fossil fuel? Because many living organisms are buried for millions of years and so on, then we can generate the fossil fuels. Even though we fossil fuels are we considering is a non-renewable, but they are technically renewable. Okay, so here when we are talking about the technological innovation, then we have to think about the energy transformation has to be approached from a technical, policy and business perspective. Nowadays you need to understand you have to make energy with a less than like a 1.5 rupees per unit and so on, because the solar energy becomes much cheaper nowadays. So we have to think about it is a technically, policy making and business perspective as well. It will be achieved largely by the accelerated deployment of the renewable energy and energy efficiency measures. Now you see these all three, all four. There are four sectors: power, industry, transport, and buildings. These are the major areas where all we are covering it, where energy is when we are generating energy or when we are creating something and we are throwing carbon out in the atmosphere, right? So this CCS means as basically is a carbon capture and storage. The green is the renewable energy, and this is the green is the energy efficiency. So this is a reference line, gives you the current these are the paths set by the today's plans and policies. So by the time, since we are talking about next 50 years challenges, we have to improve ourselves towards a green energy or renewable energy. Therefore, according to the renewable energy map, we should bring this down, reference line up to the RE map, so that this green portion can be enhanced and other contributions like the blue and all, blue also should be increased, so that we can minimize the fossil fuel cell utilization. So what is the idea into that? So you look into the power sector, the technology needs for energy sector CO2 emission reductions in 2050 compared to baseline. It means that only the power sector has ability to bring the CO2 emission much better way. So we can minimize the CO2 emission in a much better way in a power sector as compared to industry, transport, and buildings. You can see that transport is very difficult to bring the CO2. That I'm going to talk a little bit how we can contribute into direction. So if you mix it the fossil and renewable, there is a possibility that we can make a successful story. So while the mix of options varies, renewable energy can play an important role in all sectors. Okay, so this is here idea is that we have to increase the efficiency of renewable energy sources, deployment of the renewable energies, and minimizing the fossil fuels usage, so on. So what are the other options in that directions? So we have the options: wind energy, solar energy, oceanic energy, hydropower, geothermal, and biomass, and hydrogen and fuel cells, right? So these are the different renewable energy. Many people are talking about that. But some renewable energy sources in this list, such as solar, wind, and hydroelectric power, are already being used, but these come with their own problems that prevent them from replacing fossil fuels altogether. So these are the renewable energy sources, but they have some their own problems. Say for example, oceanic energy, you should have at the like better tides and so on. At the you should make it at the coastal areas only. Solar again have a different problem, but the one option, very good option comes here, the hydrogen energy. Why can't we use the hydrogen energy? We are scared. I know that hydrogen, many people are getting scared about the hydrogen and how this hydrogen can be utilized into the fuel cells to generate the electricity. So how it is? Why hydrogen? The question comes into the mind. So if you compare this hydrogen with the gasoline, the current gasoline and lead acid battery, you can see that you can't imagine this is a century-old problem, lead acid battery, but still everybody we have in our automobile, car, and our vehicles everywhere at home as well. So even though the energy density is much lower, almost 0.04 kilowatt hour per kilogram, but still we are using it. But you see that hydrogen has 38 kilowatt hour per gram. It means that if I take 1 kilogram of hydrogen, I can generate almost 1 kilowatt hour of the energy density energy. As compared to gasoline, it's more than two times. So hydrogen has the ability to create electricity by using this expression. So what would fuel cell be an option? Yes, how? You can see that when any traditional internal combustion engine start with the chemical energy like petrol, gasolines, diesels, and so on, you convert it into the thermal energy. Then thermal energy gets converted to the mechanical energy, and mechanical energy into the electric energy. So many paths we have, and we have studied that in a cyclic process only Carnot engine only we get the maximum efficiency, right? That we have studied Q2 minus Q1 by Q1 or T2 minus T1 by T2. So this is all about the engines where we are taking so many steps. By doing so, eventually you are getting a less efficiency. When you are, when you think about the tank, oil tank to the wheel, so the efficiency gets much lower. But if I employ polymer electrolyte fuel cell into the vehicle, what happens? The chemical energy directly converts into the electrical energy. That is one of the advantage of the fuel cell. You can minimize all this, thermal energy and mechanical energy conversion. So here itself, 40 to 70% efficiency can be increased compared to 30% efficiency of a traditional combustion engines. So roughly comparison of this efficiency by comparing with the traditional internal combustion, we have a promise by using the polymer fuel cell. So polymer fuels or the fuel cell has a ability to deliver a better efficiency than the traditional internal combustion engines, right? So far there are variety of the fuel cells types we have seen that, and it varies with respect to the cathode, anode, and what the electrolyte we use, what temperature we employ, what is our requirement of the power for a given application, whether it is portable or it is for stationary or it is for automobile. It varies with what is your requirement. So in all these cases, I will be talking about where I feel I am an expertise in this polymer electrolyte membrane fuel cell, alkaline fuel cell, direct methanol fuel cell, or mostly it's the low temperature fuel cells. We are looking into this catalytic part, right? So here, what is actually polyelectrolyte membrane fuel cell? I told here, this is the first one, polymer electrolyte membrane fuel cell, where we use the perfluorosulfonic acid is the electrolyte, is a membrane, which is a monopoly of the DuPont, and it works between the 50 to 100 degrees centigrade, and it can generate up to 1 kilowatt to 100 kilowatts, right? So what actually the polyelectrolyte membrane fuel cell is? So it's a very simple, it's like a battery, simple battery. You are providing fuel like a hydrogen. This hydrogen is bubbled at anode, and oxygen, which is the oxidant, which is passed at the cathode. So here hydrogen oxidizes at the anode, and the proton goes through this membrane. This is the electrolyte membrane. Here you can see these green balls are protons diffusing through this membrane, and this part where the yellow color are the electrons coming from the outer circuit towards the cathode. So this electron combines with this oxygen, where the oxygen get reduced by combining with this electron and the proton which is coming from the anode side. You can see that this blue get reduced with this yellow and green balls to form the water. So this is the air water comes. So by doing this, the circuit is completed. Here proton is going, here the electron is going. You get the electricity in the circuit. So actually a reaction looks to be the anodic is a oxidation of the hydrogen. At cathode you have oxygen reduction reaction, and overall reaction is a formation of just water plus the electricity. So this is this. I just skip this, and if you want a more actually a voltage, you can combine into the series. If you want a more current, you can combine into the parallel manner. You can get the more current as well. So this is actually not a new one. If you see that, basically the William Gore was the person who discovered this in 1839. It was the first fuel cell, hydrogen and oxygen fuel cell, and sulfuric acid was an electrolyte. This was the important commercial application of fuel cell came in 1960 when they were used and bought for the spacecraft Apollo. Gemini. So this is not a first time we are doing the research in that. It's a very old research area, but still it is an ongoing problem. So this next is very important slide. One has to understand energy conversion efficiency of automobile. So I just compare this fuel cell efficiency by comparing with the current automobiles. If I say the current automobile efficiency just give 13% of the efficiency, and I normalize this with all, so the hybrid engine gives you 35%, which is a 2.7 times higher than the current automobiles. And if I use the fuel cell at 0.9 volt, okay, minimizing the mass transport limitations and so on, I can achieve this efficiency up to 83% or 85%, 6 times higher. So any reaction which is giving more than 80%, it must be a very, very useful technology and so on. So if I apply this thermodynamics to find out the efficiency, how it comes, it's just reaction between the hydrogen molecule and the oxygen molecule to get the water. And to get the efficiency, we know the famous Gibbs equation, the delta G is equal to delta H minus T delta S, which is this minus T delta S, already you are studying the thermodynamics, which is unavailable energy, which is not being used to do the work, useful work. That is the delta G. It's a total work done, excluding the work of expansion. So the delta G of this reaction is found to be minus 2,337 kilojoules per mole, and the enthalpy of this process is 285 kilojoules per mole. And by doing the simple expression, you can find out what is the Emax of this reaction is minus delta G by 2F, which is 1.23. This number is very easy to remember. It's a 123. It's a 1.23 volt is for a single cell. And you can see that the efficiency can be find out is a 0.83, is like 83% of that. And if I add on the heat of vaporization, then I can further add the efficiency up to 98%. So this polymer electrolyte membrane fuel cell has a promise to deliver up to more than 98% of the efficiency. So why can't we use it? If I bring the hydrogen, we can use it. So yeah, now I cleared the point that it has a ability to deliver the electricity without contributing the carbon or carbon dioxide into the atmosphere. Just the product is of water, pure water, and the electricity. So these are the basic reactions in the PMFC, polymer electrolyte membrane fuel cell, and direct electronic fuel cell. The anodic reaction is a hydrogen oxidation in this case, and the cathodic reaction is the oxygen reduction reaction. And overall reaction is the formation of water by addition of the hydrogen and oxygen by the potential is 1.23 volt. Similarly, in DMFC, the anodic reaction is slightly different, which is the oxidation of the methanol, whereas the cathodic reactions is again the same one, oxygen reduction reaction. So eventually you get the oxidation of the methanol with the electricity, the potential is 1.21. So you can see here, the oxidation of the hydrogen may not be the problem. The problem, problem is the cathodic reaction. This cathodic oxygen or reduction reaction is much slower. Kinetically, is very, very slow. So it is our job to increase the kinetics of the cathodic reactions to get overall, decrease in the potential of such processes. I clear the problem. Though the reaction looks to be very simple, you can see that we have adding up 2 protons with 1 oxygen to get the water, and how to extract the energy out of this. So how to extract the energy? You can see that 2 molecules of the H2 is reacting. Now in this case, hydrogen has a 0 oxidation state. When it's formed the water, it goes to +1 oxidation state. It means that hydrogen is oxidizing. Oxygen is 0 state here. When it forms the water, it goes to -2 oxidation state. It means the reduction is happening. So basically, it's a oxygen oxidation and reduction. It's a redox reaction. And while doing so, we get the electricity. So in the reduction oxygen, we get the reduction in the potential. So when we look into the acidic condition, the 2 different mechanisms for the oxidation of the hydrogen can be written as, this is written in the reduction type. Whenever you get the hydrogen molecule in the right-hand side, in the reduction reaction, it means that hydrogen is oxidizing. I repeat again, when the reaction is expressed in terms of the reduction reaction and hydrogen molecule is written on the right-hand side, it means that oxidation of the hydrogen is occurring. So you can say these are the 2 possible reactions, but here we can choose this reaction because H+ is involved, which is the acidic media. This reaction we cannot consider because here is the OH minus ions. but the condition is acidic. So such ions cannot be generated. So we can select this 2H plus 2 electrons forms hydrogen molecule. And second one, and the other left hand side for the oxygen reduction, you can see we can write down 4 different reactions. First, oxygen reacts with the 4H plus 4 electrons form the water. And similarly, these reactions can be written as, here again we choose the first reaction where you get this oxygen reduction with the 4 electron and in acidic media 4H plus protonic. But in second case, you are getting OH minus, which is not possible, which is an alkaline condition. Similarly, here is a peroxide. So the reverse reaction in this case is a much favorable, which is called the oxidation reaction. So it is the intermediate is unstable, so we can ignore. Similar way, HO2 minus again OH minus. So this also we can ignore. So useful reactions here is the first step here, 2H plus 2 electrons, 2H2, 0, and O2 plus 4H plus 4 electron form the water. So these two reactions can be taken, and the overall reaction can be in acidic media. Anode side, it happens oxidation of the hydrogen, and cathodic side, it happens O2 reduction. Overall reaction is cathodic minus reduction minus oxidation. We get 1.23 minus 0, which is 1.234. That what we have seen in the previous slide. So this is how we select a particular reaction in a given medium. The similar reaction can be understood in a alkaline condition as well, where we have OH. In this case, the first reaction cannot be considered because it's the H plus reaction, which is not possible in alkaline condition. It is possible only in case of the alkaline. So this is the reaction where we can choose. Where the potential is minus 0.83, and in this, out of this, we can select O2 plus 2H2O plus 4 electron, which is generating 4 OH minus. So this reaction minus this reactions, what we get overall process in alkaline medium is H2 plus 2 OH minus gives us to water, and O2 plus 2H2 plus 4 electrons gives you the overall potential again 1.23. What is the inference from this? Whether you carry out this process in alkaline or acidic condition, but you're using the same fuel, hydrogen and oxygen, you are going to end up with the same potential, 1.23. You can see here it is a 1.23. You are taking the hydrogen and oxygen, but the acidic condition. And here you have alkaline condition, and we have same hydrogen and oxygen, and potential is a 1.23. So it is a matter of the reaction, what happening into the near the electrode surface. So you might ask a question, you are talking about this fuel cell and so on, so many years, 1860 and so on, William Grove has discovered this. Then what is the actually output of this? You can see this is the first commercialized fuel cell based car, which is called the Mirai, and actually it is it is manufactured by Toyota. Okay, and if you feel this fuel hydrogen into that, it requires just 3 minutes, and it can run up to 312 miles, right? Totally almost 400 kilometers, more than 400 kilometers it will run. And this is called the Mirai car, which is first fuel cell car offered for sale, not just on lease. Okay, it is commercially available, but it will take a long queue to get this car with a subsidized rate as well. Now, so what is actually another problem here? So it is the infrastructure of the hydrogen is required, that I will be talking about. So that is a more challenging. We have the technology at our door, but the problem is the infrastructure. The way what we have the petrol pumps and the diesel pumps everywhere in the country and globally, we need to develop such hydrogen pumps. So of course there are so many problems regarding the hydrogen. People have a so many worries about the hydrogen. It may create a hydrogen bomb and so on. But believe me that hydrogen is a much greener and safest gas in the in the periodic table as well. So another example of this technology where we have seen this is the development of Karodia ILH. It's a completely hydrogen-based commercial train where it is called as a world's first hydrogen-powered passenger train, which was actually launched in September, October 2018, just 2 years back. Right now, there are plenty of such trains are moving into the Germany, and which was developed by the French company Alstom. So things are moving ahead. So here hydrogen is stored in the top here, with the fuel cell next to that. So it is completely green train where we are not a single carbon is entered into the atmosphere. It's completely green technology, and which is a very recent example of the fuel cell technology is the world's first fuel cell heavy duty truck, which is manufactured by the Hyundai. We call it as Excind fuel cell. Heads to Europe. In Europe, just July, August, this July 2020. This is in the road where we have a dual 95 kilowatt fuel cell have been stacked, and two large hydrogen tanks, which are almost 32 kilograms of the hydrogen is put into this truck, which can run up to 400 kilometers in one filling. So you see that heavy vehicles also can be moved by this hydrogen fuel cell. Then definitely it has a great promise for a next generation, which is not polluting the atmosphere at all. So now where we are basically, then if you think about the PMFC to be a future technology, one has to see here that right now the current technology is this black curve, where the IT voltage versus current curves gives you this graph. If we take a little upside, this reaction can be 10%, increase one. So I can increase the kinetics of my process, right? So this technology can definitely be affordable for a common person. So our challenge is to take this current technology to the next technology where the reaction rate can be 10 times more than that. So how to do that, right? We know that this is possible by using just a catalyst. So what the catalyst does, it is again undergrad problem we have studied that. When you carry out any reactant to the product, it has some activation barrier. When you add the catalyst, this is without catalyst. When you add the catalyst, this activation barrier can be minimized. It means that catalyst is accelerating the rate of a reaction without altering the overall process, without altering the catalyst as well. It comes out as it is. So here, the minimizing activation barrier contribute to the enhancement in the efficiency of a fuel cell or any technology. So that is what. Further, then we need to consider this periodic table, and thanks to Dmitry Mendeleev, last year, 2019, actually we finished his anniversary, we call it as the International Year of Periodic Tables. This is why I gave the IYPT. 2019, almost 150 years back, this Mendeleev gave us such a beautiful representation of a different chemical element into the periodic table. Without this, it was very difficult or challenging to understand many properties of different elements. Now, among this, why this is important? Because you can see that many of such elements, like say from copper, sulfur, carbon, gold, silver, iron, tin, antimony, mercury, and lead. You can't believe that these elements were discovered. We don't know the date. Almost 10,000 years back. Even our science was not that much advanced one. 10,000 years back, these elements were discovered basically, and how they could arrange in the periodic table. So among these all elements, you can see that we cannot live without these all elements. We need a copper, we need a sulfur, we need carbon, we need a gold, silver, iron, tin. All these are very essential commodities of our day-to-day life, which were discovered 10,000 years back. And after that, from this, I said this carbon, almost 10,000 years back, this carbon being a very important material, as I said in few slides back, I said that carbon is a problem in our day-to-day life. Carbon is a problem and carbon is a solution as well. I will tell you why. Because we cannot live with carbon, we cannot live without carbon. It is very, very important. Then another very important element in the periodic table is the platinum, which is a noble material which cannot be affected by many chemical reactions. And these are the focus of our material in the next few minutes to go down. Okay. So why the platinum being selected as a catalyst for such reactions? Right now in fuel cell, platinum is being used. So what are the essential criteria? It should have a high oxygen absorption capacity. It should be structurally stable and during many reactions. It should be stable with electrolyte medium like acidic condition, high alkaline condition. It should have ability to decompose peroxide intermediate. It should have a very high conductivity. It should have a high tolerance toward the methanol, and very important is a low cost to get it afford for a common person. So these are the different noble metals being employed for this fuel cell technology. And why platinum? It has a special characteristic like a high work function, ability to catalyze the reduction reactions of the oxygen. It has a very good resistance to corrosion and dilution and high exchange current density, which is the best characteristic of a platinum. That's why we are going to use this platinum into fuel cell, where the platinum is the only element being used in the fuel cell in a cathodic reactions. So what are the challenges actually for the PMFC technology? So these technology hurdles are, first one, the overpotential in both the cases in hydrogen oxidation and oxygen reduction reaction case. I said that is the oxidation of hydrogen and reduction of the oxygen. In both the cases, the overpotentials are very high, even though if I use the platinum. Then cost due to platinum and polymer membrane. Of course, you know that platinum is very costly. Polymer is also very costly. It's a DuPont monopoly. Then the cost of the hydrogen production. Right now we don't have a better way of production of the hydrogen. Storage is again a problem for the hydrogen, and polyelectrolyte stability and activity. These are the various problems for the hurdles of the fuel cell. And it's a typical IV curve where you can see that first area where we can call the activation barrier. Second one is the ohmic barrier, and last one is the actually concentration polarization or the mass transfer region. So because of this, eventually you are ending up with the potential is less than 0.4. You can see this potential 0.4. What is our expectation? It should be 1.23, which is the ideally, theoretically, or thermodynamically reversible potential, 1.23. But because of so many losses, you are ending up 0.4 fold with a high current density. So we have to minimize this. So I said that this curve should be like this eventually. So at least we can get up to 0.8 or 0.9 fold continuously with the existing conditions. So why it is happening so? So you can see that there are various reactions happening here. So the overall potential of this fuel cell is basically then irreversible. It's 1.23 minus all the losses like resistance because of electronic resistances, membrane resistances, HOR overpotential, ORR overpotential, and humidity conditions, diffusion, so many. These are so many losses. Because of that, we end up with E cell, which is much lower than 1.23. So we have to work on it to give a better technology. So our area of expertise is this area where we can call as activation barrier to minimize the overpotential because of the hydrogen oxidation and oxygen reduction reaction. So these are the another list of problems for the technology. The dependence on the water, the polyelectrolyte problem is the dependence on the water for its conductivity. It's very important. High fuel permeability or the crossover effect is a problem. Tendency to get disintegrated by hydroxyl ions. These hydroxyl ions, because of the Fenton types of the reactions, it dampens the polyelectrolytes and it gets corrodes. Then lower thermal and mechanical chemical stability at various operating conditions of this polyelectrolyte makes technology much problematic for the future applications. So this is another how to go, because when we are starting the research in this area, then you might ask me how to work in this fuel cell area. So this is a basic area where you can start in your laboratory. If you have a potential step, you can start with a recording such voltammogram. We call it cyclic voltammogram. It gives you the total surface area of the platinum, how much your platinum is exposed, and how is the platinum surface is going to give you the activity. So this is a typical voltammogram run on a platinum surface or platinum nanoparticles. Okay, so these are various regions where we can understand what is the reaction is happening. And then after that, in half cell reaction, these are the reactions where we can get at a different rotating disk electrode, and you can run this ORR polarization curves, and this gives you the EHAP reactions, and this gives you the onset potential. This onset potential again indicates you the reversible potential. What we were explaining to 1.23, it gives this information. So this half cell reaction can be run in the laboratories. Once you feel that this curve is moving to more and more positive side, it is actually good catalyst. It has a less over potential, and then you can take it to the stack level or actual fuel cell level. But in the laboratory, you can do this. This is not difficult at all. In our lab, my laboratory, it is a rigorously such reactions are, we are doing it in the laboratory. Okay, so this is a basic reactions to be tested in the laboratory before going to test it for the fuel cell. That I will give one example on that. So this I skip here. So here main problem again, developing such catalyst is we have the platinum catalyst on the carbon support, and during the course of usage of this catalyst, what happens? Sometimes this carbon get corroded because the potential of this carbon is lower than this OER reaction. Therefore, this carbon can be dissolved, and along with this carbon, there is a possibility that platinum also can be lost. And then we cannot afford the loss of the platinum. So we have to secure the platinum. Again, there is a possibility of getting oxidation of this platinum. It means there's a corrosion of the platinum may take place. Some places, this migration of the platinum small particles will take place to get it in a coalescence, or it is called as the Oswald ripening, the agglomeration, and so many problems are happening. So when you are running a vehicle, when you are using this fuel cell, by applying this platinum on the carbon catalyst, there is a possibility that all these reactions can happen. This carbon dioxide will form because of the carbon oxidation. So we have to make such a catalyst which can minimize such all problems. We can stop the corrosion of the platinum, we can stop the corrosion of the carbon, we can stop the coalescence of these particles, and we can stop the Oswald ripening as well. Then it will be a good story. Then such catalysts can be used for a technology for a longer run. So how to do that? How to achieve this goal? To get a good efficient fuel cell, there are two different things. One is a catalyst, right? To generate a best catalyst for minimizing the over potential, and second one, the membrane. So membrane can be generated in such a way that fast proton conduction can happen without water or low humidity condition. So this is a complete different area where the polymer electrolyte can be synthesized. And our area is to discuss about the generating new platinum catalysts to form low oxygen spaces at high voltage region. When you form more oxygen on the platinum surface, there is a possibility that platinum get dissolved, get oxidized, and it dissolve into the electrolyte. So that we have to minimize. While doing so, many people have done that. They added some transition metal into the platinum, and they get this activity increase with respect to the addition of a different transition element, because nickel, iron, cobalt, these are the elements which are cheaper in nature. If you add into that platinum content, just 50% of the platinum and 50% of the cobalt, iron, nickel gives you the much better, stable, active material for the oxygen reduction reaction. So this is our expertise, where you can see that kinetic current density is increasing with increasing addition of the nickel and iron. When it reaches to a maximum where the composition of the platinum and transition metal is almost same. Why it is happening? You can see that when you increase the content of iron, say for example, I am taking an example of the iron, start adding the iron into the platinum bulk, what will happen? This is the increasing donation ability. What is the donation ability? The electron is given from oxygen to the platinum will increase. It reaches to a maximum where the donation and back donation are same. But when further increase in the iron content, what happens? The back donation ability will decrease. And once the back donation ability increases, what does it mean? Once the electron is given to the platinum has to give back the electron to reduce the oxygen, to break the oxygen bond. That is, if that is not happening, then that is not a good story. So your bonding between the oxygen and platinum molecule like this should be optimum to get just absorbed on the platinum, get a coordinated bond, then transfer the electron from oxygen to the empty PAT orbitals, then give back to this oxygen back, so that the bond between oxygen and oxygen get broken, to get the platinum intact without any oxygen, and you get the H2O. Once it forms the H2O without leaving any oxygenated function group on the platinum, it is a good story and it will be a good material. So which is possible only in case of where we have 50% of the platinum and iron. Such materials, we have later on found that these are the L10 phase or super lattice structures, or it is like chemically ordered structures. So what are these chemical? So this is our aim is to go up to the structure which looks like a very super material PT3Ni 111 surface, this sputtered material, which is very difficult to make as a catalyst, but our idea is to reach up to this. But all our activities of other metals are very less. So here there are two different mechanisms. It's a 2-electron transfer process mechanism and 4-electron transfer mechanism. So it is again, one has to find out, the good story is to get the direct 4-electron transfer rather than the 2-electron transfer. If you get the 2-electron transfer process, you will end up with the peroxide. Or this is the peroxide. So peroxide is not a good story because peroxide generates OH radicals in presence of iron and such elements, which deteriorates the membrane. So our idea is to get only the water molecule in a one-step reaction, 4-electron transfer in a one single-step reaction. So these are the basic, some literatures and how people have done this. These are the state-of-the-art reports available. But I will explain this. What are the actually superlattice trimetallic compound? If some of you are master students or PhD students would like to work in this area, actually this is a very wonderful area. Only the concerns of our students will be getting a platinum, right, precursor. So here, say for example, 50% of this different combination of the manganese, iron, cobalt, and copper we are going to add in the platinum. Then, which decreases the platinum-platinum distance. When we decrease the distance between the platinum-platinum, the formation of oxygen to the platinum bond will be intermediate, so that it donates the electron and takes the electrons very fast. It means that the reduction of the oxygen is a much better way on such surfaces. So this was the idea where such structure formed by this method is the order structures. We call it the face-centered tetragonal structures. And when you don't treat that as a superlattice structure, then these are the disordered structures. So disordered structures and order structure, what is the difference here? In a disordered structure, the elements are randomly mixed in an abscissa manner. But in ordered structures, we have along the C-axis, we have alternate PT and transition metals are stacked. And along the A-axis, we have mixture of platinum and transition metal. Why we call it order structure? Along the C-axis, we have alternate PT and transition metal elements. That's why these are order structures. But symmetry has been lost. So we have seen such structures along with the combination of the platinum, iron, and copper. We see that their activity is much better in even fuel cell conditions. You can see here the potential is almost 0.9, more than 0.9, and which is sustained up to 60 hours durability. But later what we found out that such material, when we have iron or cobalt in structures, that catalyzes the reaction like a peroxide, OH radical formation, which gives the OH radical. This OH radical will be forming in a Fenton type of the reaction where Fe plus 2 or copper plus reacts with the peroxide to form the iron plus 3 and copper plus 2 with the generation of the OH radical. This generation of the OH radical will affect the membrane, and once it affects the membrane, it will deteriorate the output of the fuel cell. So by considering this problem of the iron-based compound, then we move to the how surface structure affect the catalytic performance by taking the cobalt and nickel along with the platinum. So this was actually we published in this Nano Energy, and also we patented. The patent was granted in India, and we filed for the US patent as well. So we have arranged such cobalt and nickel in such a way that in some salt manner, so that we find a superlattice structure of the nickel, cobalt, platinum. So how it does? How we understand this superlattice structure? You can see that these new peaks are forming here, 110 and 001, along with 002 and 210. The formation of this superlattice structure indicates the formation of such order structures. So now, what is the benefit of using such order? You can see this dotted line indicates the platinum only. In the case of the platinum, these peaks are not available. But when it is order structure, these peaks are going to form, and the extent of these peaks or the facets gives you the extent of orderness in our structure. So these are the all different models we have done, how the activity is higher, and we can just compare the activity of both the commercial platinum C and our catalyst. It looks to be like a 95-volt positive shift for our PT to CONI, as well as the activity, specific activity and electrochemical surface area is also very, very high. And eventually what we have seen here, when we are trying to synthesize any material, we have to see their stability. Most of the time what happens in the laboratory, we test a material which gives a very good activity and efficiency, but after a few cycles, the activity goes down. That is not a good story for a practical application. So what we see here, with the different cycles, the activity is further increasing. This is because of several reasons that we have proved by using the exhausts and our surface analysis by using XPS and so on. And it gives our information that it forms the hollow structures like a frame-like structures with a different scanning. And this is the reason why the platinum along with the cobalt and nickel gives you much stable structure for high surface area. And again, I said that when I test for the peroxide formation, it should not form the peroxide, as I mentioned that anything less than 5% peroxide formation is a best catalyst for the fuel cell application, which gives, you can see that the number of electrons transfer is a 4 electron transfer for the throughout the process. Very stable 4 electron transfer process indicates this is a worth catalyst for a fuel cell application. Then we have seen that such application in a fuel cell. We tested this material for the fuel cell. This is a fuel cell fabricated in our laboratory. We can see that this is a MEA, membrane electrode assembly. It is called. This is the next step after the lab testing. So here, similar loading done for the PT2CONI and the commercial platinum C. It gives you. You can see that this black curve is commercial and red is the PT2CONI. It gives you much stable performance in a much lesser humidity, indicating IB performance is comparable. But when you see about the ISCA, electrochemical surface area, is a retention. You can see that we have retained its electrochemical surface area in much better way, almost 80% than compared to the K.B.P is a commercial platinum catalyst. So it means that our catalyst is much stable than the commercial platinum available in the market. So this again a durability test. What we have seen, even 10,000 cycle, it looks very stable. So the conclusion of this, the slide gives you the PT2CONI shows higher durability comparable to TKK-PTC, means the commercial PTC, and with less amount of the platinum used, because 50% is a platinum, 50% is a transition element. It means that it's a good story. Without losing the activity, we are generating such a catalyst, beautiful catalyst, which can be used for a fuel cell application. So after this, we tested structurally. There are several changes that we are seeing in more details. Some partially transparent to platinum. The trimetallic alloy remains remains even after 10,000 cycles. There is not much change in the particle size, just 4.4 plus or minus 1.1. But you can see the commercial platinum, how it gives 5.5 to 1.8 plus or minus nanometers. There are a lot of agglomeration in commercial catalysts. So apart from that, I will take another just 4 or 5 minutes, then we can stop here. So that was, I was talking about completely platinum-based catalysts. So many of our such groups are available where we want to avoid completely the platinum. If we avoid the platinum, we can minimize the technology costs in a much better way, much higher way. So these are some catalysts or some materials which are like analogous to graphene, like HBN, hexavalent boron nitride. Here, idea is that in the graphene we are not matching the atomic positions on the top. It's just slightly tilted. That's why we can use use them as a lubricant materials. But HBN, no. All exactly the elements are matching on one another. It means that we have this anything hollow throughout. So there is a possibility that hydrogen molecule can diffuse through this boron nitride single or bilayer. Okay, so this is about a very crazy idea. What we decided here, we can oxidize the hydrogen on one side and we can reduce the oxygen on the other side. It is a very crazy idea in a very miniaturized way. And here the diffusion of the hydrogen can take place and we can construct a nano level fuel cell. So for that, then we have seen that boron nitride has a very, very wonderful practical applications. That's what this, the title gives you. When inert becomes active, this HBN is very inert, is insulating more than 6 electron volt, is a band gap. Then when we tune their structure by altering their characteristic, we can generate a fascinating characteristic for such material. Then we can use them as a catalyst. So we have published almost 10, 15 papers in that direction. So, but still we feel that we are very near to the results where we can expect what actually the boron nitride is doing here. So apart from that, these are the various materials which the recent generation can be interested in generating energy related materials like graphene, HBN, metal organic famers, carbon nanotubes, C60 magazines, where we are also working rigorously on magazines, different metal nanoparticles, MOS2 and so on. And with that, we are working in several areas in our laboratories. Almost 7-8 students are working rigorously on that. And we feel that we are very near to development of such materials which are used for the fuel cell applications. And with this end, I should talk about the hydrogen is the only next economy, and we have to find out its sustainability as well. So hydrogen has a very high potential for the energy sources. We should make what is the objective of our laboratory and fuel cell energy related research area is that we have to save the energy. We have to show the public how the fuel cell vehicles are efficient, how the hydrogen energy is very useful, how emissions of CO2 gases will be reduced, how they are harmful for the society. And we have to raise the public awareness about the fuel cell application, fuel cell vehicles. We have to create a new sources for the renewable energy, and we eventually the takeaway message is the slow down climate change. We have to minimize the climate change. We have to minimize the carbon footprint in our atmosphere. And at the end, I should stop with the quote given by the Herman Coopers, which is a Royal Dutch Shell. He says that we are at the peak of the oil age, but the beginning of the hydrogen age. Anything else is an interim solution. The transition will be very messy and will take many technological paths, but the future will be hydrogen fuel cell. We have only hydrogen to answer for many problems, right? So we are in the middle of the fossil and renewable, and we are confused. So we have to make our ideas clear. But remember, my friends, the hydrogen is only the future. So we have to think about generation of hydrogen in a greener way as well. So thank you very much. You are welcome to our group, and you can look into our activities. Anybody is interested in future, they can contact me. So I will be happy to answer your questions. And thank you very much.
Thank you, sir. Very well said that it will be a future aspect. Dear participants, you are requested to drop the questions in the chat box, or you can unmute yourself and ask the question.
Hello.
Yes.
Hello, sir. Thank you very much for such a beautiful and informative session on fuel cell. Sir, my question is that how one can confirm that your electrolyte is passing H plus and not electrons? Means suppose I am dealing with
It's a very simple
suppose I am dealing
question.
with
And a simple problem, and it's a very routine problem we are dealing with to check the polyethylene membranes, whether it is electronically conducting or is a ionic conductor, right? That is your question.
Yes, sir. Yes, sir.
Yeah, this is basically two techniques. You have the electrochemical impedance spectroscopy to take the what is the conductivity of protonic conductivity. You will understand the proton conductivity, but you may get very slight information about the electronic conductivity. So you can do the 4-probe measurement, IV measurements to check the electronic conductivity. That is a much easier way to take whether it's electronic conductivity or what.
Thank you. Oh, thank you very much, sir. Thank you.
Yeah, you're welcome.
Do you have any question, participants? Sir, actually, I have one question.
Yeah.
As I am working on solid oxide fuel cells,
Yes, ma'am.
I'm using their solid materials only. But if I will think about this polymer exchange membrane fuel cell, as it is a membrane,
Mhm.
do you think about the strength of the material? Or how do you measure the strength of that electrolyte?
So you mean to say the electrolytes for the SOFC? Are you,
PM.
what kind of strength you are asking about the mechanical
This
strength or thermal strength?
mechanical strength.
For mechanical, then there are several tools. You can when we talk with the mechanical people, mechanical engineering people, they have several tools. The tensile strengths can be measured. That is no problem. That is very again very routine research people we are doing it. When we are doing in a polyester membrane, we make a different thickness, different dimensions. We measure the strain and strength effect, and we can talk about their um, different parameters where that membrane get detached or any deformation we get it. We can test even microscopically also after the breaking the membrane. And of course, the microscopically we can see by doing microtoming TM as well. So micron level understanding can be also done. So there are several measurements or basic measurements can be done to get more fundamental research in this area.
Thank you, sir. Ulka ma'am, do you have any question?
Hello, sir. I'm having one general question. Is like now fuel cell vehicles are coming in market. So, what is the scope for fuel cell research in future? Means,
See, one very big challenge here it is hydrogen in this fuel cell research area. Right now in India, the hydrogen is generated. Hydrogen is just a byproduct of many industries like hydrocarbons and so on. So it is just a byproduct, and it is going to the atmosphere. Since we are using in the laboratory, there and there only we are getting a hydrogen. Otherwise, hydrogen is not being used anywhere else. So, but since it's a byproduct, we are using it. But once we start the fuel cell actual technology being developed in the country and globally, uh, the production of the hydrogen is again a very big issue. Say, for example, many people are coming up with the problem solution with the electrolyzing water, like a water splitting. But you can say almost like a 10 times more energy you're putting into split the water and get the hydrogen, which is not like a feasible again. So we need, say for example, so we have to find out such a better way to produce hydrogen and mostly the onboard hydrogen production.
yes.
So this is one of the areas where you can focus it. And again, still, there is a problem where completely eradication of the platinum is not being done. So if you find out such a material which completely replaces the platinum, will be a huge success. We are doing it. Like people are looking into carbon-based materials and so on. We get in the laboratory level, but for longer cycles, it doesn't hold the current what the metal-based catalyst holds. That's why that is another challenge where to make completely platinum-free materials. So that is one of the again area which gives many papers, publications, and many PhDs as well. And what is actually happening? Still, many technologies being developed. All are platinum-based, like 40%, 43% platinum loaded, which is very highly costly. Almost 100 grams of the platinum in the combustion engine, which is completely non-cost effective compared to 5 grams of the platinum-based element in the combustion engine. So, complete removal of the platinum is not possible, but one has to look into that area. So we cannot avoid that. We cannot find that there is no alternative for platinum. Right now, there is no alternative for the platinum. If you find out some alternative to the platinum, that is another one discovery for this or the game changer for the fuel cell technology.
Okay, sir. Okay. Thank you so much.
As there are no further questions, thank you, sir, for the excellent talk.
Thank you
Now
very much,
let's
madam.
move towards our next session. I request Dr. Suraj Harad to introduce our next speaker.
Thank you, ma'am. Good afternoon, all. Okay, it's my great pleasure to introduce our next speaker for this one-day international seminar on energy storage and decompression devices, Dr. R.S. Kalvarne. Professor R.S. Kalvarne is currently working as a scientist in Center for Materials for Electronics Technology, Pune. He had completed his BSc degree from K.B.P College, Pandharpur in 2000. He has completed his post-graduation from Shivaji University, Kolhapur in 2004. He had received a senior research fellowship from the Council of Scientific and Industrial Research, New Delhi in 2007. He had completed PhD from Shivaji University, Kolhapur in 2010. He worked as postdoctoral fellow and as a research professor in Channam National University, Gwangju, South Korea. These research topics include development of lithium-ion, lithium-air batteries, supercapacitors, development of sodium-ion secondary batteries, development of ceramic substrates, glass ceramics, lithium-ion conductors, and thin film physics. Till now, he has published 72 research articles in reputed national and international journals. He has published 2 books and filed 1 patent. He has presented 36 research papers in international conferences. Now he is working as a scientist in CMET Pune and working on energy storage devices. Please welcome Dr. R.S. Kalvarne, sir.
Thank you for your kind introduction. May I request Dr. Kapde to just stop its presenting mode so that I can load my presentation. Am I audible?
Yes, sir.
Dr. Kapde, sir, please just.
Yeah.
Thank you. Thank you. Is the presentation visible?
Not yet, sir.
Okay, just let me know.
Yeah, it is visible.
Okay.
Yes.
Okay. At the outset, I would like to thank the organizers for giving me the opportunity to present my work in front of the students and the faculty of this college. The title of my talk is Metal Oxide Based Advanced Energy Storage Devices for Renewable Energy Future. So the outline of my talk is the introduction, and then renewable energy perspective in terms of Indian context, then metal oxides for energy storage applications. I would like to just brief about 3 chemistries of battery, like lithium-ion battery, then metal ion battery, and just I will give the glimpses for the supercapacitor, and at the end I will summarize my presentation. So as earlier in the earlier presentation, sir has given the details about the 10 important problems of humanity in next 50 years. And he already discussed about the how energy is important for the human. So I will skip this one. And now you can see high energy. So as we also discussed about that, the renewable non-renewable energy sources are now going to end in near future, and we need to depend on the renewable energy sources like biomass, solar energy, wind energy. So you can just in this plot you can see the how the energy requirement for the world is projected. So in within a 10 to 20 years, the amount required or the requirement of energy will be doubled for the world. So we need to have the more energy from all the sources that are available with us. So this is the how this fossil fuel or oil prices are increasing. So that we need to shift from oils to the renewable energy sources. Like these are the different kind of renewable energy sources that we can have. So now, if we talk in terms of the potential of these renewable energy sources in context of India, so if we can see that solar energy that we can take from is 750 gigawatt, wind energy 100 gigawatt, bioenergy is 25 gigawatt, and hydropower is 20 gigawatt. So, what are the policies that have been made by Indian government to use these renewable energy sources? In that way, Ministry of Non-Renewable and Renewable Energy Sources is playing a proactive role in promoting the adoption of renewable energy resources by offering various incentives such as generation-based incentives, capital, and interest subsidies. The National Solar Mission aims to promote the development and use of solar energy for power generation and other uses, with the ultimate objective of making solar energy compete with fossil-based energy options. The establishment of dedicated financial institute, the Indian Renewable Energy Development Agency, that is IREDA, makes for renewable inputs on the promotion, development, and extension of financial assistance for the renewable energy and energy efficiency conversion projects. So now, if we can see the what is the capacity that has been installed in India. So currently, till November 2020, the total energy distribution stand at 90 gigawatt for total installed capacity of 369 gigawatt in the country. The government of India has set targets which will take the total renewable capacity to almost 175 gigawatt by the end of 2020. This includes 60 gigawatt from wind power, 100 gigawatt from solar power, and 10 gigawatt from biomass power, and 5 gigawatt from small hydro projects. So, however, these renewable energy sources are intermittent; they are not constant. You cannot find solar light continuously. It may be discontinued. Same in the condition from the wind and other sources. So it requires efficient and distributed electrical energy storage on scale ranging from public utilities to miniaturized portable electronic devices. So if we consider the different kind of energy storage technologies, there are capacitor or supercapacitor, batteries and fuel cells. So fuel cells gives the high specific energy or energy density, but it cannot give the specific or high specific powers. Supercapacitors are the materials that give high specific powers and low energy density. So batteries are the materials which can give the moderate specific power and specific energy. That's why people's and it is easy. It is directly conversion of chemical energy to the electrical energy. So it is easy. So it can avoid the thermal mechanical part in between, so that you can get maximum efficiency for these devices. So these are the advantages of these batteries and supercapacitors. Batteries possess specific energy higher than supercapacitor, low temperature dependence, unlimited cyclability, slow charging discharging, and use of toxic chemicals make batteries unfriendly to. This is the disadvantage of the batteries that we can avoid by developing the environment friendly materials. For supercapacitor, it generates powers ranging 10 to 100 times of batteries. It also have the low temperature dependence, unlimited cyclability, fast charging, and environmentally more friendly. So, why metal oxides? If you can consider the metal oxides, it gives advantages like low reaction voltage, high capacity, and relatively low cost. So these are the different materials that have been used for batteries, like lithium-ion batteries and sodium-ion batteries. So now for batteries, there are two different types. One is the metal-aid battery, in which lithium or sodium is used as a anode material, and cathode is the oxygen, and which can react. If you can see, this is the these are the reaction at anode, in which lithium or sodium reduced to give the lithium or sodium ions, and the oxygen from the environment at cathode reduces to form the oxygen ions, and it will react with the lithium or sodium metal to give lithium or sodium peroxides, which can be stored in the cathode. So the other battery is the metal ion batteries, in which lithium or sodium metal ions stored in the anode and cathode. They are moving from anode to cathode and from cathode to anode reversibly to give the electricity. So now the current outlook of this is the currently the lithium ion batteries are being used in the already commercialized electric vehicles, but the energy density of lithium ion is limited by intercalation chemistry. The energy density of lithium ion is in the range 100 to 150 watt hour per kg. So these are the limitations. So in order to increase the energy density of the batteries, so if you can see the metal layer, that is lithium ion, lithium air battery, have the energy, theoretical energy density comparable to the gasoline, which has now we are using for fueling the our transportations like car or heavy vehicles. So hence we are the research is going on for the metal air batteries. So these are the battery chemistries over the years. Initially, in the batteries have been developed in 1859, which is lead acid battery. From that, it's been changed. That chemistry has been changed to the nickel hydride and nickel cadmium batteries. Then after nickel hydride, nickel metal hydrides. Then the lithium ion is being discovered in 1990. And now we are working on the enhancement of the energy density by replacing the cathode like LiCO2 by their counterpart like lithium phosphate and the silicon. These are the anode materials have been developed or being developed, and the future batteries are the lithium oxygen battery and lithium organic batteries. So if you can see that this is the basic principle of lithium air battery, in which at anode lithium is oxidized to give to form the lithium ions, and at cathode oxygen is reduced to form the oxygen. So there are two different kind of reaction occurring at cathode depending upon the byproduct, that is whether it is Li2O2 or Li2O. Based on that, the final potential of the battery varies from 2.9 volt to 2.7 volt. So these are the potential. These batteries have the potential to run the electrical vehicle for longer. So this slide will give how the actually oxygen is reduced at cathode and lithium ion oxidize at anode to form the Li2. This is a kind of discharging reaction happening at cathode. At the end, you make that final product is the lithium peroxide, which is gets stored in the cathode, which is the porous material having the catalyst. What are the importance of catalyst and why it is being used, that we have already heard from earlier speaker. So I will not give the details about that. So in the charging process, the lithium oxide is being converted into the oxygen by decomposition of Li2O2, forming the oxygen, and it is being given to the atmosphere, and the lithium is being plated at anode. So now let me tell you what are the challenges in lithium air battery. So the main challenge is the overpotential due to the inefficiency of electrocatalysis. So there are two different reactions like oxygen reduction reaction happening at discharge process, and oxygen evolution reaction or nothing but the decomposition of the byproduct generated during the discharge process. And due to this, the total efficiency of this battery is less than 70%. So other challenges are, so in the lithium ion batteries we are using the electrolytes. Those are when during the discharge process the oxygen is produced. This oxygen reacts with the electrolyte and forms the carbonates or decomposes the electrolyte. So due to the decomposition of the electrolyte, the battery is getting dried, and hence the total process of the charging discharging stops. The third one is the porous carbon or the cathode structure. So for getting deposition of the product that is formed during discharge, that Li2O2, we need the porous structure of the cathode so that it can accommodate maximum Li2O2, and which lead to the higher capacity. And another one is the electrocatalysis. So in electrocatalysis, due to the formation of this O2, it will react with the electrocatalysis also, and it will reduce the electrocatalytic activity of the catalyst. So these are the main challenges are in the air electrode. So what are the challenges? The reaction products are formed on the cathode surface, and cell polarization is mainly due to the cathode. So non-aqueous lithium energy falls far short of the theoretical values because the discharge terminated well before all of the pores in the air electrodes are filled with lithium oxides. So how to solve it? To solve this issue, we have to develop new cathode materials that can accommodate large amounts of oxides. Additives to improve the solubility of the precipitate, that is Li2O2, in the electrolyte, so that the decomposition of the Li2O2 during the charging will become easy, and develop the catalyst that alters the morphology of the lithium oxide deposits. So this is the general process to make the battery, in which we have to make the material first, and then processing to make the phase pure. Then these will be grind or mixed with the conducting materials and vacuum mixing. Then these materials will be coated on the conducting substrate or like porous structures like nickel foam for making the air electrode, and then roll press to make the densification, vacuum drying. Then we have to cut the electrodes in the desired format and make add the electrolyte, and then finally we will crimp it or make the cell in the desired shape. And after the final is the battery analysis. These are for lithium oxygen cell. We need to have the holes at the cathode side so that oxygen from the outside it will be diffused to the cathode, and it will react with the lithium in the discharge process. For lithium ion or metal lithium or sodium ion, the cell assembly is closed. So start with the first material that we have developed as a catalyst for lithium ion battery is the zirconium doped ceria. Why we have choose that the cerium oxide, commonly known as ceria, is very attractive for catalytic application owing to its oxygen vacancies. Due to these oxygen vacancies, this oxygen is get attracted to these vacancies, and it can easily convert from oxygen molecule to the O2 minus phase that is required for reaction with lithium. So ceria is an active catalyst that enhances the reactivity of the another metal as well. So these zirconium doped ceria materials have been prepared with combustion process. You may be knowing the combustion process, but for your information, most of the metal nitrates of precursor were dissolved in the water along with the fuel, which may be glycine or urea. They have been uniformly dissolved and then further heated to form the gel. At certain temperature, this formed gel is autocombust and forms the desired product after the combustion process. So after this, you can see we may have formed the phase pure zircon doped ceria, and we have also seen the porous structure, because for air cathode, porous structure of the material is a main requirement, so that the deposit, that is Li2O2, is get stored in that, and we can get the maximum discharge capacity for this material. So further, we have characterized these materials for the XPS so that we can understand what are the oxidation state of the cerium found on the surface, because cerium formation of Ce4 to Ce3 plus is required so that oxygen deficiency can be found in the ZDC, and we can get the easy absorption of O2 on the surface for electrocatalysis. So in this, we can, after zirconium dipping, the C3 plus on the surface of ZDC material were 14%, which will enhance our electrocatalysis. If you can see, this plot shows the charging discharging for lithium air cell, in which this black curve shows for only without catalysis. We have not used the catalyst on this air electrode. But when we use this our catalyst on this, then you can find that the polarization for the charging discharge also reduced, as well as it gave the higher discharge capacity, and charging also. The efficiency has been improved with the efficiency of the electrocatalyst. So we can see that these are the Li2O2 found after discharge. And after that, after recharge, this Li2O2 formed. These are the ZDC particles, and this has been removed after charging. So these there are two different processes to charge discharge of lithium ion batteries. In which one is the full discharge to the full discharge, and in another one is the limited discharge. In which, so because if we even discharge up to the 100 milliampere hour per gram, we can achieve the high energy density, because for lithium ion batteries the capacity of one cell or LCO is around 120 to 150 milliampere per gram. But if we can achieve the capacity up to 1000 milliampere hours per gram for our lithium ion cells, and the number of cycles that we have got is 40 cycles. This is due to there are some issues related to electrolyte also, because if we use the carbonate based electrodes, then those carbonate based electrodes get decomposed and form lithium carbonate, which is very difficult to decompose, and so that we are not able to recycle our lithium air cell to the full extent. So what is the reaction mechanism? How? So if you can see, this is the CV from which you can get the how our electrocatalyst works. So at this potential, oxygen reduction starts in where the oxygen inserted will react absorb on the our catalyst, and it will convert to the due to this C forms the intermediate Ce4 plus and O2 minus, and then further it reduces to O2 minus and reacts with the lithium single ion to form LiO2, and for in second step for the then it will convert into the Li2. So these are the different reactions that are at the cathode. So for charging reaction, this is Li2O2 get directly dissociated to form Li2O2, and then it converts into lithium and by giving the electrons. So another material is the lanthanum nickel cobalt oxide. So why we have chosen the same principle we have is there. So by replacing the cobalt 3 plus in the LaCO3 by nickel 2 plus, we can create the oxygen vacancies. So it will help to absorption of oxygen, and it will enhance the electrocatalytic activity of the our lithium cobalt oxide perovskite. So we have prepared these perovskites by using the simple combustion process, and this we can see that by XRD it is phase pure material and porous structure consisting of small connected nanoparticles. So further we have studied the charging. So in this experiment, what we did is that we have combined this perovskite material along with the commercial Li2O2, so that we can understand how efficiently this perovskite material is decomposes this Li2O2. If you can see, the only without perovskite, the capacity or the decomposition obtained for the Li2O2 is only up to which will give the capacity of 200 milliampere hour. But if we use the perovskite along with the carbon, then the potential for the decomposition of the Li2O2 also reduce, as well as it could decompose or give the capacity up to more than 1000 milliampere hour per gram. So how we observe that whether that lithium oxide is decomposed or not? This is the Raman plot for the electrode before charging, and after charging you can see that this LiO peak at around 780 centimeter inverse. So it has been completely vanished. That means this Li2O2 available in the electrode is completely decomposed, and so we can that perovskite is more efficient for the ORR reaction. So in that So now we have developed one cell including this lithium metal as anode and air cathode including our perovskite material. And this is without uh, catalyst. You can easily see similar to the previous case for where without catalyst material we cannot achieve capacity more than 1500 milliampere per gram. But when we increase or when we added this perovskite, then the decomposition potential or the polarization for the cell is reduced, as well as we can achieve the capacity above 6000 milliampere hour per gram. So by using the catalyst, we have increased the Coulombic efficiency for LiO2 cell from 59% for without catalyst to 98%. So that in this way we can enhance the catalytic activity of the material by tuning the its structure. So these are the reaction mechanism. So it is the similar to that of the ZDC, in which oxygen is adsorbed on the oxygen vacancies of the phosphate material and forms the intermediate of O2 minus, and then it will react with the lithium to form Li22, and then further it disproportionate to form the Li2, and then similar is the case for the charge. So when we studied the continuous cycling of this lithium air battery at constant capacity of 1000 milliampere hour per gram, in comparison to the ZDC, we are able to, or we have increased the cyclability of our cell to 49 cycles while maintaining 1000 milliampere hour per gram under the limited capacity. The excellent electrochemical properties of perovskite, the combination of the fast kinetics of electron transport provided by the carbon support, and the high electrochemical activity for electrode oxidation provided by the layered perovskites. These are the reasons why we are getting the good performance compared to JDs. So we have analyzed these materials of a cell for impedance, and we can see that how the impedance of our cell changes from pristine to first discharge, first charge, and then after 20 and after test. We can see that there is no much change. There is only change after 20 discharge, but after test it is retaining to a slight change in there. So that indicates that our material is not changing or decomposing. So it retaining its structure, and we can get the good performance of this material. So now in lithium-air batteries, we are the air electrode composed of the carbon material and the catalyst. But if you can see, there are some disadvantages of using the carbon material, because when the carbon is used, this oxygen coming from atmosphere reacts with the carbon to form and the lithium to form lithium carbonate. So it will hinder or it will reduce the catalytic activity of the catalyst, as well as it will dry up the electrolyte, so that it will hamper the your cyclability of the material. So for that, in order to overcome the disadvantage of carbon, we thought that why not use the carbon-free electrode, which is the freestanding catalyst. So we have, for that we selected the manganese cobalt oxide material, and these are the spinel materials considered as electrocatalysts for oxygen electrodes due to their high catalytic activity and good corrosion stability. The presence of two solid-state redox couples, that is CO3 plus and CO2 plus and Mn4 plus and Mn3 plus in the structures, enables the spinel oxide to exhibit a remarkable electrocatalytic activity. So in order to make the freestanding electrode, what we did is we used the hydrothermal method, so that we can deposit or grow our electrocatalytic material directly on the substrate, that is nickel foam. So for in this process, what we did is that we have taken the nickel foam as such. After that, we have etched this nickel foam so that any oxides found during its we have kept for that. So maybe if there is oxide is there, we can remove with the etching. And after that, we kept those nickel foam in the hydrothermal reactor. So in the initial process during hydrolysis, the seed layer of the precursor of the nickel manganese hydroxide has been formed, and then it further grows in the rod-like structures. Further, if we extend the hydrothermal process, then the rods form will get agglomerated or rearranged to form the spheres. These spheres have been grown on the rod-like structures of manganese cobalt oxide. These are the hydroxides. In order to make this hydroxide into oxide, we have to give the heat treatment at around 400 to 450 degrees centigrade, so that this hydroxide has been need to be converted into oxide, so that we can achieve the good activity for the catalyst. So, how we decide the temperature at which we have to anneal the hydroxide so that we can get it converted into oxide. So, for that we recorded the TGDT, and we can see that at around 432 degrees centigrade, that the hydroxide is getting converted into oxides. So, if you can see that this is the pristine, these are the hydroxide peaks, and at 425 we can get some hydroxide peaks at presence also, and less crystallinity. But at 450 you can get highly crystalline material with good peaks. So if we see the microstructure of MCO, we can see that this is the nickel foam, and on this these are the nanorods grown on the nickel foam, and further extension of the hydrothermal process, we can get the spear-like structure of the nanorods, which are get deposited or grown on the these nanorods. If you can see, these are spear-like structure, and you can see this yes, high-resolution PM image gives that confirms the formation of MCO, that is manganese cobalt oxide. So now we have what we did is here we did three different composition, in which one is the pure carbon, another one is the we have mixed this manganese cobalt oxide along with the carbon and coated on the nickel foam, and the third one electrode is the freestanding electrode. So if you can see that for cobalt the polarization is higher, with the addition of our catalyst the polarization has been reduced, but for the freestanding electrode, we can achieve the minimum polarization and the capacity above 10,000 milliampere hour per gram. So when we studied this at different current specific currents applied, then we can see that this freestanding electrode or cathode gives the higher capacity for higher discharge capacity for the lithium metal. So for this we have recorded the morphology of the Li2. So we need to see, but whether there is any effect of morphology that has been found during the discharge on your catalytic activity of the material. So if you can see, this is the SCM of cathode taken after the discharge. We have to deassemble the cell and take the cathode, arrange it with the electrodes so that any decomposition electrolyte precursor, lithium precursor is there, it will be removed, and we can get the clean surface to observe the structure of the Li2O2 has been deposited. You can see the toroidal-like structure of Li2O2 is found on the carbon-containing cathode. But when we see the freestanding, then we can see that this Li2O2 is get coated on our nanorods, and it covers the entire structure of the rod. So in that way, so due to the presence of carbon, the structure or the microstructure of Li2O2 that is forming is different than the freestanding electrode. So we have seen that how we have checked that whether which material, whether it is Li2O2 or Li2O is formed during the discharge process. We found that it is Li2O2 is the forming during the discharge process. So now this is the schematic for the oxygen reduction reaction mechanism. How the Li2O2 is get formed on our nanorods. So if you can see for these rods, there are oxygen vacancies found due to the different states of cobalt and manganese. So this oxygen is get absorbed on these deficiencies, defects, oxygen defects found on these nanorods, and further it will grow in linear side or along the rod side to cover entirely the rod. So in the reverse, so this coating forms the different morphology. So it will give the that it is very much connected with the rod. So during the decomposition, it is easy to decompose these Li2 from on the nanorods. So when we cycled these MCO at constant capacity, then we can observe that for only without catalyst material, we can cycle up to 20 cycles. When we added this the carbon with the catalyst, the cyclability extended to 50. And when we use the freestanding, the cyclability extended to around 120 cycles. This is nothing but we can predict that due to the carbon, so we can avoid the formation of lithium carbonate by using the freestanding electrode, and hence we can extend the cyclability of the lithium air cells. These are the third discharge curves for that freestanding and without with carbon electrodes. So after that, we have analyzed with the electrochemical impedance, and you can see for the pristine it is less after discharge due to the high resistance of Li2, the impedance of the material or the cell increase up to 20, and then after charge it comes to the origin. That means the entire Li2 that has been deposited or found during the discharge process is being converted into the oxygen and lithium, so that this further for the electrode will be ready for the next cycle. So after that, so we have seen that even by using the freestanding electrode, we cannot get the cyclability more than 120 cycles. Now, in order to see check what is the reason behind the failure, because we have avoided the carbon, even though we have avoided the carbon, it is the lithium air cell is being stopped at around 120 cycles. For that, we have reassembled the cell and seen the air electrode. So we found that there is no change in our air cathode or the freestanding electrode. So it is we can get the similar morphology as we have found during the pristine or the fresh electrode. So then we have taken that electrode and we have used the fresh lithium and fermented cell and recycled or cycled it, then we can get the cycles. That means there is no issue with our air cathode. So what is the issue then? Then we have studied the lithium surface. So if you can see, this is the pristine or fresh lithium surface. Sorry. This is the fresh lithium cell, and this is the surface of the lithium after 120 cycles. You can see that after Raman analysis, you can observe that there is the formation of lithium hydroxide or lithium carbonate on the surface. This restricted the flow of lithium and the reaction with the oxygen. And due to this reason, the formation of lithium hydroxide and lithium carbonate, our cell becomes dead. So this is the reason. So we can, if we can avoid the ingress of this may be due to some in the oxygen coming from surrounding or atmosphere, it may contain some carbon dioxide or water. Due to that, it reacts with the lithium and forms lithium hydroxide in the lithium carbon. So that for making the cell, we needed the membranes. Need to use the membranes which are not only will allow the oxygen and which will restrict the entry of water or CO. In this way, we can improve the cyclability of our lithium air cells. So now let me tell you the another chemistry, that is lithium ion and sodium ion. So this slide will show you how the lithium ion and sodium ion charge and discharge. Actually, for lithium ion and sodium ion, the anode and cathode are the materials which are the compounds of either lithium or sodium, depends upon the chemistry that we are studying. So those lithium ions or sodium ions are stored in their structure, and during charging and discharging, they are moving from anode to cathode, and the electrons related to that reaction will flow from the external circuit, which will give you the current. So if you can see now, these lithium ions are moving from anode to cathode, and you are getting the current. This is the discharging state. So in the charging state, we need to give the potential across the battery, and during that process, what happens? The lithium ions stored in the cathode will migrate to the anode by consuming the electrons from the external source. In this way, charging and discharging of the lithium and sodium ion batteries takes place. So this material is being used as an anode material for lithium ion battery. This material is the manganese dope cobalt oxides. So why I have chosen the cobalt oxide is because this material has the high specific capacity of 890 milliampere per gram, and it will react with the 8 lithium ion to form 4 Li2 and 3 cobalt atoms. But this material has some limitations like low or poor electrical conductivity. So due to this, we need to add some conducting additives. Due to that, the total capacity of the material will reduce. So in here we have adopted the doping with the
Excuse me, sir.
manganese. Yes.
Your screen is not.
Not. Whether now it is visible?
No, sir.
Yes, yes. Now
Yes.
it is.
Huh?
It's visible now.
Okay. So these are this cobalt oxide is used as anode, and so we have chosen this due to its high capacity, but it is having the low electric conductivity. So we have tried to dope this cobalt oxide with manganese so that it can improve the electronic conductivity, increase cycle life, and improve the stability of the material. So the combustion synthesis process is used for the making this manganese dope cobalt oxide, and this is the similar process that I already discussed. So after that, we have varied the composition of manganese from 0.1, 0.2 for cobalt. So you can see this is the three different structures, and you can face pure cobalt oxides. But due to the addition of manganese, there is shift in the peak at the lower angle. That means the lattice parameter of the material is changed. So particle size obtained for the 0% Mn is 100 nanometer, and for that for 1%, 0.1% and 0.2 Mn is around 15 nanometer. So when we make this electrode and made the hub cells along with the lithium as anode, so we have for testing any material, we have to make the hub cell with the lithium, in which our material under test is acts as a cathode for that, and lithium is acts as an anode. But actually, this material is the anode material for the fuel cell if we consider the battery. And we can see that the charge discharge capacity for the 0.1 ml doping is increased from 1027 to 1428, and discharge capacity is also increased to 1041 milliampere hour per gram. So in the cathodic scan, these are the peak related to the conversion of CO2 into CO and Li2, wherein this lithium reacts with CO3O4, oxygen from CO3O4, and it forms Li2O, and cobalt metal is formed in the on the electrode surface. And this is this peak at anodic scan is due to the formation of when this oxygen from Li2 reacts with cobalt to form cobalt oxide. And at this stage, this cobalt oxide is ready for the next charge cycle. So the next step is to study the cyclability, long-term cyclability, and rate capability. So for rate capability, what we do is that initially we will discharge the cell with a low current, and then we increase by step to the higher C, where now C is nothing but 1C is the amount of current required to discharge the electrode or material to its full within a 1 hour. That is the amount of current required is the 1C. So we can see that if we see the 20C, that means the battery will discharge within a 6 or 3 minutes. It will fully discharge or charge. That is that much amount of current we are applying here. Even that also we can get the capacity more than 600 milliampere hour per gram. But the more important thing is when we increase the current and when we reduce the current, the capacity retention should be there, so that we can see that here at around when reversal of current at 0.1C, we can get the similar capacity for this manganese dope cobalt. And you can see the cyclability. This electrode is cycled up to 200 cycle with the capacity more than 100%. If you can see that the initial cycles, the capacity is around 1,200, but at around after 200 cycles, the capacity is around 1,300. That means, so this is due to nothing but activation, because in initial stage, the lithium ions are not moving or not using the entire area of the electrode. As the charge discharge goes, or the then it diffuses through the electrode, and it can use the entire electrode, and we can achieve the capacity. And we have observed the stable capacity up to 200 cycles. So after that, we have made a fuel cell, including the LiCO2 is the commercial material used as a cathode, and our MnCO3O4 is used as a anode. And we can see that the capacity more than 140. For the first cycle charging, it is 159, and discharge is 144 milliampere hour per gram. So in this way, we have demonstrated that the manganese dope cobalt oxide is being used as a anode in the lithium batteries. The cyclability also stable. We have achieved stable capacity up to around 130 after 100 cycles. So the next material is the nickel titanium oxide. This material is used as the anode material for sodium-ion batteries. So why we have selected this? Because this is NTO is an ilmenite structure that comprises layered transition metal octahedrons. Like you can see, this is the NiO6 octahedron. It is arranged in the zigzag manner. So these are the open tunnels that are available for the storage of sodium in this structure. And further, in addition to the store of sodium in the structures, it will undergo the reaction in which, so conversion reaction, in which nickel titanium oxide reacts with 6 sodium to form the nickel titanium and this sodium oxide. So in addition to that, that means few molecules will store the sodium, and few may take part in the conversion reaction, it will give to the additional to the capacity of the material. So for this, we have used the hydrothermal process in which nickel and titanium precursors were mixed and with the reaction promoter and kept in the hydrothermal reactions to form the nanoparticles of the nickel titanium. So if you can see the particle size of NTO is around 3 to 5 nanometer. If you can see small particles, we can observe here, and so we can see the composition whether that availability of nickel, titanium, and oxygen in the structure of the material. So further, we have in addition to XRD, Raman is the best tool to form study the crystalline nature of the material. So if you can see the different modes of the Raman for NTO suggest that highly crystalline nature of NTO. And we have further analyzed the surface area by using the BET, and we can have the type 3 isotherm with S3 hysteresis, and which can give the surface area of 39 meter square per gram. And the total pore volume for this material is around 0.37 centimeter per gram. So further, we have made the electrode of this cell and assembled the cell using the sodium metal as anode and this as a cathode. And we can see this is the reaction for sodium insertion in the NTO, and this is the removal of sodium from its structures. So these are the redox peaks, repeatable. You can see the repeatability of the CV, which gives the good repeatability of this material for the sodium storage. So discharge gives the at hot temperature, at hot potential, the reaction start. If you can see, this is the similar at around 0.7. It's 0.5 or 0.7. It starts to insert into a structure, and it continues till it's completely fill the structure. And the discharge capacity of 783 for first discharge, and first charge it is around 520. That means around more than 70% efficiency is obtained for first cycles. And as we can see, for further cycle, the efficiency of discharge or the sodium insertion essential increase more than 95%. So further, we have studied the read capability by applying the smallest current of 50 milliampere per gram and the highest current of 4000 milliampere per gram. So you can observe that this material also shows the good read capability at higher current. Also, it can give around 200 milliampere hour per gram of specific capacity, and when we reduce the current, it can retain its capacity to its fullest. So these materials are cycled at two different currents, at low current and high current also. You can obtain at a high current and low current, you can retain more than 95% of the capacity over 200 cycles. So impedance analysis is required to study what are the changes that are taking place during the charge discharge. So this is the before and this is the after. We can deconvolute these different parameters of the impedance like electrolyte resistance, film resistance, charge transfer resistance, and capacitance for this. You can see that for first it is, and there is no change in the electrolyte resistance for the cell throughout the testing, while also for film resistance the same, and the charge transfer resistance also remains almost same. That means this, due to this no change of the electrode has been occurred, and this resulted into the stable cyclic performance of the NTO for the sodium storage. Now just to show you the supercapacitor, one material that is cerium oxide and CNT composite that we have made by using the hydrothermal process. And so this is the schematic for making the hexagonal CO2 material on the CNT. We have made that reaction to happen at pH greater than 7, and you can see that from TM the hexagonal CO2 is decorated on the CNTs. So phase purity and the presence of CNT as well as CO2 is also seen. and the CNT formed is around 10 to 20 nanometer in size. So we have tested this. This is CV for CNT, bare CNT, bare CO2, and this is for composite. So we have observed the capacitance values for CO2, CNT, and then two different composition of CO2, CNT, where we have varied the composition. So for CO2 it is 87 farad, for CNT it is 156, and for two composite, for first composite it is 282, and for second composite it is 234 farad per gram respectively. The symmetric cell with C1, and then this is the charge discharge for the symmetric cell formed using the C1, that is first composite, and which exhibit 289 and 262 farad per gram. While the C2 exhibit 234 and 167 farad per gram for the symmetric cell. So we have cycled these cells up to 300 cycles respectively. So these are the cycling stability of C1 and C2 materials, composites. So only 7% fitting is there for C1 cell, while that 28% fitting is there for C2 cell. So the corresponding this capacitance is converted into the power density and energy density. So we can see that the energy density observed is around 30.9 watt hour per kg for C1 composite, and that for another composite is 22.4 watt hour per kg. At the same time, the specific power achieved by the symmetric supercapacitor cells are 21.2 kilowatt per kg. In the summary, the significant improvements in the performance of LiO2 cells reported herein are attributed to the tailored properties of materials, which are vital to catalytic reactions, including the exposed oxygen vacancies, effect sites, porosity that enables good diffusion of electrolyte and oxygen to the active sites, and the high conducting network of the carbon graphene support. The metal oxides can also be used in lithium and sodium ion batteries with high energy and power density and excellent cyclostability. The fissile hydrothermal technique can be used to fabricate CNT metal oxide nanocomposites and design supercapacitor devices with high energy and power densities and excellent cycling stability. The main part is that metal oxide nanostructures have potential application in energy storage devices or renewable energy field. Thank you.
Thank you, sir. Dear participants, you are free to ask questions. Please write question in your chat box, or you can ask. Sir, I have one question.
Yes.
Can we use carbon-based materials for sodium-ion battery?
Yes, actually for carbon-based material, we need to have the only graphite which is used for lithium-ion battery, which is having the stacking structure. As the lithium is having the low ionic side, it can easily go into that structure and it can easily come. But if we consider the sodium, the ionic side of sodium is large, so that it is not possible to move or the insertion of that sodium in the graphitic structure. But if you can convert that carbon into the hard carbon, in which the interlayer spacing of your graphitic structure is increased by hitting it or making the hard converted that carbon into the hard carbon, then that hard carbon can be used as an anode for sodium ion batteries. Most importantly, you have to change the graphitic structure of that particular carbon material. So you have to increase the interlayer distance between each graphite layer, so that the sodium ion can be easily inserted and extracted during the charging and discharging process.
Is there any question? Is there any question, participants? Yes, sir. Yes, sir.
Hello, Varme sir.
Yes, yes.
Thank you for a very nice presentation. I have just one question, sir.
Yes, please.
Sir, have you ever tried carbon electrodes generated from biomaterials?
So we have tried, we have not yet tried, but there that may be the potential area wherein we can generate the carbon, and we can, the main application for this biomass derived carbon is in the supercapacitor, because for supercapacitor carbon is the best suitable material. We can tailor the surface area as well pore structures. So, but for, if you consider for batteries, so it may be used in the lithium, but for if you want to use for sodium, it needs to be graphitized or make into the hard carbon, so that the interlayer spacing, as I told, that interlayer spacing between the graphitic structure can be enlarged to that easy movement. But best application for the biomass derived carbon is the supercapacitor.
Sir, actually, one of my students, she is working on carbon electrodes
Okay.
generated from biomaterials.
Okay.
And actually, she is having some binder issues.
Binder.
Binder is kind of, after evaporation, there are some cracks to the electrode. So we are not able to get a uniform and solid electrode material.
Oh. So what kind of process that you are adopting for making the electrode?
Actually, we have taken rice husk for carbon as a carbon material.
Okay.
And then we dissolve that material into 1,3-propanediol.
Okay.
And we have used PTFE as a suspension binder.
Okay.
That's it. And after the evaporation,
okay. Instead of PTFE, why not use NMP PUDF mixture? PUDF you have to dissolve in NMP, either NMP or DMF. Make
which one, sir?
PUDF, polyvinyl difluoride.
Okay.
You can dissolve it either in NMP and methylene pyridone or dimethyl formamide. Either of these two you can take as solvent, dissolve the PUDF and make add your carbon into that, make the slurry, and you can coat it, and you can just heat at around 80 to 100 degrees centigrade under vacuum, so that you can get the uniform lines without any cracks.
Okay, sir. We will try with this solvent.
Yeah. Yes.
Okay, sir. Thank you very much.
Is there any other question? So in the chat box, Mathad sir have asked, suggest some good fuel cells.
Suggest some fuel cells.
Fuel cells, yeah.
Actually, fuel cells, I am not that much expertise. Actually, Dr. Kakade will be the best person to whom you can contact regarding this. I can tell you about the batteries, but I am not expertise in the fuel cells. So as you maybe missed the earlier lecture on fuel cell by Dr. Kakade, you can contact to him, then you can get the idea from him.
Thank you, sir. If you don't have any question, participants, let's move ahead for the next session. I request Dr. Kamlesh Chandekar to introduce our next speaker.
Hello. Good afternoon, everybody. It is my pleasure to introduce our resource person for today's seminar, Dr. Abhishek Lokhande. Dr. Abhishek Lokhande, who is currently working as a postdoc fellow at the Khalifa University of Science and Technology, Abu Dhabi, United Arab Emirates, UAE. He obtained his PhD degree in 2019 in Material Science and Engineering from Chonan National University, South Korea. Before that, He obtained his bachelor degree in 2012 and master degree in 2014 in mechanical engineering from Shivaji University, India. His research interests includes synthesis, characterization, and development of novel efficient metal colgogenide nanomaterials for thin films, solar cell, gas sensors, and energy storage, energy conversion system. He has published over 90 high impact factor review research articles, including 7 review articles, 2 book chapters, 1 book on the thin film solar cells, and has obtained 5 patents, 2 from South Korea, 3 from India. Recently, in 2020, he was elected as the Young Associate Fellow of the Maharashtra Academy of Sciences. It is a brief CV of Dr. Abhishek Lokhande. Over to Dr. Abhishek Lokhande.
Yeah, thank you. Is my voice audible?
Yes, yes.
Yeah, thank you for your kind introduction. So, first of all, everybody. So today I would like to give my presentation about my research. So the topic is on supercapacitor materials. So let me just start my presentation now. Is my screen visible?
Not yet, sir.
No,
Not yet.
not yet.
Is it visible now?
No, sir. Yeah, it's
Yeah,
Is it visible?
now it's visible.
Okay, okay. Okay, so I will start my presentation. So it's based on chalcopyrite based carbon composite electrodes for high performance supercapacitor applications. So currently, I will just give a brief introduction. I'm working as a postdoctoral researcher in Khalifa University. So this work was conducted in this university, and the project was sponsored by our university.
Abhishek sir,
Yes, sir.
just a minute. I cannot see your screen at present.
You cannot see my screen?
Yeah. Actually, I can just see screenshot, but I think there is a sharing option and it is not shared completely.
sir. Just you have to open your file first, or
Yeah, it's open.
yeah, you can click on the that file first. Then it will be visible.
Yeah, okay. I have opened. Is my presentation visible?
Actually, your window is visible.
Yes.
Good afternoon, ma'am. Yes, I can hear you now. Yes, you are audible now. Yes, no problem.
Is it visible now?
Not
No,
yet.
Abhishek sir. Now it is, I think, opening.
Yeah.
Yes.
Yes, it is visible.
It is visible, right?
Yes. Now make it presentation.
Okay.
Yes.
Okay, thank you. Okay, so today I will going to present my research based on supercapacitors, especially on the use of chalcopyrite based carbon composite materials for supercapacitor application. So presently this work was funded by Khalifa University of Science and Technology. So I will just start with my presentation part. So before starting with the actual results, I will just give a brief overview about the energy storage devices. Is my voice audible?
Yes, sir. Yes.
Yeah, okay. So let's discuss in brief about the energy storage devices. So I think most of the part Dr. Ram Karbune sir has explained it very well. So I will just explain in brief about these energy storage devices. So basically, energy storage system is it is a kind of system in which we can store and discharge a charge, or in other words, we can say we can store energy and then we can release it over a period of time in a controlled manner. So this is what we are calling as a charging and discharging cycle of an energy storage device. So energy storage device, as discussed before, and as we can see here, it consists of like four important systems. The first one is fuel cells, the second battery, the third capacitor, supercapacitors, and the fourth one are the traditional capacitors. So what is the difference between a battery and a capacitor? Is that so the charging and discharging time in the supercapacitor is very fast, so we can charge it very quickly and we can discharge it very quickly. Also, the cyclic stability of the capacitors is very good, and the power density is higher than the batteries. In case of batteries, the energy density is high, but to be very frank, the research now is completely focused on enhancing the power density and the energy density at the same time. But however, we cannot achieve all these two parameters in one system, either in battery or supercapacitor. So the research is still going in this field. So basically, if you see the supercapacitors in this Ragun plot, they just form a bridge between batteries and conventional supercapacitors. So our goal is to enhance the capacity, and that through in coordination with increasing the energy density and power density of the system. So as we can see, the important features for capacitors are like maximum power density, maximum energy density. They should have a long cyclic stability. They should be very easy and handy, and they should have a smaller volume so we can accommodate it at any places. And they should have very low internal resistance. Of course, the features completely match with that of the current lithium-ion battery technology. So let's discuss about the basics of the supercapacitor. So tradition, if we can see in this slide, the capacitors are classified mostly in three types. The first type is electric double layer capacitors. In this case, the working mechanism is slightly different compared to other its counterparts form. The second one is the pseudo capacitors, and the third one is a mixture of electric double layer capacitors and pseudo capacitors, which we call it as a hybrid capacitors. So in case of double layer capacitors, especially all the carbon based materials, they exhibit this type of charge storage activity, that is electric double layer capacitance. So they just store the charge on the basis of electrostatic charge. On the basis of electrostatic charge, suppose if we give a negative charge to carbon based material, they can easily hold up a positive charge based ions on its surface. In case of pseudo capacitors, the working mechanism is totally different. In this case, the charge storage and charge discharge usually occurs through Faradic chemical reactions. So especially in this case, the electrolyte ions, they interact with the electrode materials and they undergo some chemical changes, and through that a charge is stored or a charge is discharged in our capacitors. And when we combine both of these electrodes, or when we combine this both mechanisms, it forms a hybrid capacitor. So especially if we see the applications of supercapacitor, just like batteries, it has many industrial applications, but the major requirement of capacitors is mostly in electric vehicles and in mobile flash system, and like in taser guns or in medical health systems. So in that case, a sudden burst of energy is required for the applications, and this can be satisfied by using supercapacitors. So let's discuss about the materials which are used for the capacitors. Of course, the materials, they form the backbone of any electrical device, though it may be like a battery or a capacitor. So the proper selection of material is always important. So up to now, as we can see, there are certain class of elements that have been reported for capacitor application. So the first class is carbon-based material. So this carbon-based material consists of graphene oxides, carbon nanotubes. Then the second types of metals are conducting polymers, that is polyaniline, polypyrrole, as we say. And the third one are the transition metal oxides and hydroxides. And the fourth one are metal sulfides and selenites. Of course, there are transition metal sulfides and selenites. And the important reason why we should choose the transition metal oxides or hydroxides, especially in battery and supercapacitor, because they have multiple oxidation state. So if we can exploit their oxidation properties, oxidation state properties, definitely we are going to get good charge. So let's see about the requirement for the supercapacitor electrode material. So definitely the surface area of the electrode metal should be high as possible, so that we have very good interaction with the electrolyte ions. The electrical conductivity also matters. It should be always high as possible. And the electrode should be stable in terms of its chemical and mechanical stability, because we are subjecting it to numerous charging and discharging cycles. And also, very importantly, it must be easy to synthesize and it should be cost effective. And very important, the material which we are going to choose for a capacitor application, it should have reversible activity. It means that if that person, if that electrode undergoes any charging or discharging cycle, it should switch to its oxidation and reduction states rapidly without degrading its performance. So let's discuss about the materials and some of their disadvantages, especially for carbon-based material. Though they have very good surface area and good conductivity, they have some disadvantages. Are very costly to synthesize, and their energy density is low. So especially in case of supercapacitors, if we are using aqueous based electrodes, definitely we are going to get low voltage output as well as the power output. In case of conducting polymers, they have stability issues, and these stability issues are mostly related to its hygroscopic nature. That is, these polymers tend to absorb moisture from the air, and they tend to undergo some chemical changes. So this significantly affects the performance of the capacitors. And in case of transition metal oxides, they have very good stability, but being an oxide material, and they have plenty of oxygen content in their crystal structure, it hampers their electrical conductivity. So these are some disadvantages of the electrode materials, and what we need to do is we need to find a suitable material that overcome all these disadvantages and can really prove a viable material for future applications. So let's see why we selected metal sulfides, or why metal sulfides can be preferred for capacitor applications, because there are certain properties which we should consider. So basically, metal sulfides are very inexpensive, and they have stability as similar to that of metal oxides. Second thing, the metal sulfides have unique physical and chemical properties, especially being a sulfur content in their structure. It enhances the electrical conductivity. Also, it forms a tetrahedral bond with its surrounding elements, so it gives good thermal and mechanical stability as compared to the metal oxides. Uh, the metal sulfides are also rich in redox chemistry, so it definitely contributes to higher capacitance, especially due to their multiple oxidation state. They can generate an more amount of charge, and if you compare with the carbon-based material, it's definitely several times higher. And the next thing is the natural abundance of these metal sulfides is very large, and we can synthesize it, and they at a lower cost. And if we compare the toxicity, Definitely, all the electrode materials are toxic, but some of these metal sulfides, they are less toxic as compared to others. Also, when we fabricate metal sulfide based electrodes like binary, ternary, or quaternary compounds, definitely the synergistic effect of this metal sulfide oxidation state is going to enhance the electrical performance. So in this case, we have finalized and we have selected uh, metal sulfide that is called as copper iron disulfide as a material for supercapacitor applications, as it contains two metals, copper and sulfur, and we thought of exploiting their oxidation states, and we thought to explore their electrochemical performance for supercapacitor applications. So let's discuss about the background of this copper iron sulfide. So this copper iron sulfide is also known as chalcopyrite materials, and this compound is used for copper extraction. Almost 80% of copper is extracted from this compound. It is cost-effective, earth abundant. It is readily available. If we consider their optical properties, yes, they have optical properties, but if you can see the band gap is quite low, 0.2 to 0.6. So we cannot exactly call them as a semiconductor because their band gap is low. So it means they have very good conductivity. And the important thing, they form a very good tetrahedral bonding between the elements. That is, sulfur forms a tetrahedral bonding with copper and iron, and this definitely gives mechanical and electrical stability and conductivity. And they also exhibit some ferromagnetic properties due to the iron content. So based on these properties, researchers have demonstrated the application of this compound in very versatile fields such as dye-sensitized solar cell, image system, dielectrics, sensor system, biological system, electro-water splitting, lithium and sodium ion batteries, and the last part which we have explored is the supercapacitor part. So this was the background of the supercapacitor and the electrode material, and how we selected the electrode material, and how we have acquired the application part of this electrode system. So next, I will directly proceed with the experimental details. So we prefer to go for hydrothermal method because hydrothermal method is very easy, and we can synthesize the compound with unique morphologies. So one thing we should always keep in mind that if you want to use any electrode for battery or supercapacitor application, it should definitely have a good surface area. So and naturally the hydrothermal method produces electrode with unique morphologies, especially flower like or a high surface area. So we selected this method and we tried to synthesize the chalcopyrite material. So in this case we use some salts, metal salts like copper chloride, iron chloride, and thiourea as a sulfur source, and we mixed it in water as we use water as a solvent, and we conducted the experiment at 160 degree for 12 hours. So to be honest, the hydrothermal step is a single step and binder free. So we do not need to use any kind of binder to prepare the electrode, as we can directly use any substrate in the autoclave during synthesis, and we can directly deposit it, and we can directly use as an electrode. So once we have synthesized it, we characterize it with several techniques. So in this case, we try to synthesize, we try to deposit the material on substrate. So in this case, we have used graphite paper as our working substrate. So if you can see, this is the graphite paper, and after deposition, we can after hydrothermal treatment, we can see directly the chalcopyrite material is directly deposited on the graphite paper, and we also checked the adherence of the material on the substrate, and it was quite good. So we were very happy that we at least have got a direct synthesis of material on the substrate, and we confirmed some we confirm using some of the techniques like the X-ray diffraction and XPS analysis to confirm whether we have formed the compound, desired compound. And yes, of course, we have formed a desired compound, which we have confirmed from the XRD analysis and as well as from the XPS analysis. And if we can see the XPS spectra, especially for copper and iron, we can clearly see the existence of copper and iron is in +1 and +3 states respectively, and sulfur is in -2 state. That's okay, but we are very much interested in copper and iron oxidation state, and if you can see, they do have multiple oxidation states. So this is going to be very interesting because we can use their oxidation states to exploit for supercapacitive performance. So we further characterize the material using some FESM and high resolution TM techniques, and also we did some elemental mapping. So if